Yes, thank you. So, good evening to all the participants. So, welcome to the SPARC online workshop on CO2 refrigeration systems. And
your figure
now,
is your photo is not coming. Only welcome is coming. You can okay, carry on.
okay. So now
Okay, carry on.
I would like to request Professor MP Maiya to address the gathering and to give brief introduction of the workshop. Professor MP Maiya, sir. So, floor is yours. You can take.
Continue. Do you want to continue? Stop others screening. Continue. Okay. And now.
Yes.
My screen is visible. Sorry, fundamentals. Sorry. My welcome to visible.
Yes, sir.
Welcome to workshop.
Yes, sir. It's visible.
Okay. Good. So, greetings from IIT Madras. Good evening, good morning, wherever you are. Good evening and good morning. Thank you for registering this workshop. This workshop, CO2 refrigeration systems, fundamentals, advancements, and applications, is being organized under the aegis of SPARC project. SPARC project, sponsored by MHRD Government of India through SPARC management or SPARC scheme of projects. SPARC is the scheme for promotion of academic and research collaboration, in short SPARC, aims at improving the research ecosystem of India's higher educational institutions by facilitating academic and research collaborations between Indian institutions and the best institutions in the world from 28 selected nations to jointly solve problems of national and international relevance. Our project is the performance enhancement of CO2 refrigeration system with thermal energy storage for the Indian dairy industry. And it is our partner collaborating institutes are IIT Madras, IISc Bangalore, and NTNU Norway. And I welcome all of you on behalf of the collaborating institutes and my project coordinators, Professor Pramod Kumar, Professor Armin Hafner, and Professor Trigve Ekwit. So on behalf of all project coordinators and collaborating institutes, it is my privilege and honor to welcome you all to this workshop on CO2 refrigeration systems, fundamentals, advancements, and applications, being held for the next today and next 4 days, 10 to 14th October 2022, in the evening hours 4 to 7 p.m. It is in online mode. I welcome all of you. Coming to the workshop, you can see that it is being organized online for 5 days from today to Friday. 5 days in the evening time, 4 to 6. 3 slots in each day. And there are 15 lectures. In fact, 16 lectures one day. One slot, 2 are will be giving in the last day. There will be, in fact, 16 lectures by eminent personalities from the institutes, faculties of in the institutes, from the industry, from the research institutes, from what you call non-governmental organizations, the Center for Fisheries Technology, and various people, including very young, bubbling with energy, the postdoctoral fellows on the last day. You can see various aspects of carbon dioxide refrigerant systems are covered in this course in the next 5 days, in the evenings of next 5 days. And basically, you can see the applications are huge for carbon dioxide systems. Right. Dairy institutes, food refrigeration, hospitals, hotels, data centers, kitchens, low temperature refrigeration, and so on and so forth. Most of the things can be covered, but not all. Each refrigerant has got its territory. So we will be explore what all carbon dioxide can do, and I'm sure you will appreciate after listening to all these lectures the validity or the scope of carbon dioxide refrigeration. Certification: the e-certificate shall be issued to the registered participants and subject to more than 80% attendance in the workshop. Okay. I don't know whether we will be having the formal concluding sessions where we can thank people. I take this opportunity to thank right now. First is, I would like to thank the SPARC management and the MHRD, Government of India, for sponsoring our project and this workshop. I also thank my fellow project coordinators, Professor Armin Hafner, and Professor Pramod Kumar from IISc, and partner institutes, NTNU and IISc and IIT Madras. I also thank EduCool and Indie Plus projects with whom we got the support, and also ISRE, the Indian Society of Heating, Refrigerating, and Air Conditioning Engineers, for supporting the workshop. I should thank all the resource persons who would be giving their expert lectures in the next 5 days. I would like to thank Dean ICNSR, Dean Global Engagement of IIT Madras and their staff, especially Lisa, Edil, Vinod, and Rupa Madam. I would like to thank all the PDS under Indie Plus project, and in particular Dr. Y. Sivakumar Reddy, who is responsible for taking up this workshop and almost handled single-handedly. I would like to thank all the participants who have registered to this workshop and would be attending it, which is essential for the success of the whole workshop of the event. Finally, but not the least, I would like to thank all those helped directly or indirectly in organizing this workshop. Thanks for your attention. So with this, I'll go to my talk now. I'll stop sharing. This is visible now. Fundamentals and relevance of CO2 refrigeration.
Yes,
Yes,
sir.
sir. It is.
Okay.
Visible. Yes, sir.
Okay. Thank you. Okay. Again, good evening. Good morning. I will talk now about the fundamentals and relevance of carbon dioxide refrigeration under this workshop: CO2 refrigeration systems, fundamentals, advancement, and applications. Okay. So this SPARC online workshop is being held from 10th to 14th of October 2022 in the after evening hours 4 to 6 in 7 each day. There are 3 slots. Now this lecture is being delivered day 1, 10th October, slot 1, 4 to 5 p.m. or 16 to 17. I'll be talking now with fundamentals and relevance of carbon dioxide refrigeration. I'll be delivering this lecture with the 45 slides, roughly 1 slide a minute, and then I'll be able to complete with the 45 minutes. So level of learning, especially in my lectures of 45 slides, is all of you know Bloom's taxonomy. As you go up, the learning process becomes tougher and tougher. Bottom you see remembering and knowledge. Next is understanding and comprehension. The third level is applying and designing. And in my lecture, I'm not definitely go below above that. Definitely, I'll be basically first 2 levels easy. So don't worry. I say easy. It will be easy lecture. Just remembering some knowledge, understanding and comprehension, and you can nudge towards application and designing. You can try yourself. Nothing beyond that. So it will be easy. Okay. Now, my presentation outline is as follows. Okay, I don't know. Not going. My photo. Okay. My full screen is visible, right? Hello. My full screen is visible.
Yes, sir. Yes, sir.
The right hand corner, Dr. Y. Shivakumar Reddy is not coming, right?
It's visible, sir.
Then why can't you delete that? How to delete? Because my full screen will not be visible, no? Okay. No. Okay. I'll push it to side. Okay. Okay. Good. No. How is this situation? Okay. Good. A presentation outline. First will be introduction and learning objectives. Takeaway is what is present day apprehensions, importance of cooling in India, refrigerant selection criteria, and finally, why is CO2 coming back? Researching, coming back. Second is simple transcritical vapor compression refrigeration system, VCR cycle. Under this, you will be able to know what is Carnot refrigerant cycle, what is conventional VCR cycle, CO2 properties and its advantages, transcritical CO2 cycle, then why is COP of simple transcritical cycle is lower than its contemporaries or synthetic refrigerants. Basically, you have to identify the losses. Third is modification to simple transcritical CO2 cycle. And under this, you will be able to know how and what modifications will improve COP. Something like internal heat exchanger, gas cooler pressure optimization, intercooling, intermediate pressure, and subcoolings, and ejectors, expander, so on and so forth. Finally, relevance, applications, and future trends and summary. Under this, you'll be able to identify possible applications in anticipation of future trends. So this is my presentation outline. Coming to introduction now. You see, what is the artificial cooling was invented very recently, maybe 125, 150 years back, comparing to our whole computer. It is about 65, 70 years back. So compared to that, no, a little older, yes, but not too old. 150 years ago, is a natural ice is equal to refrigeration. If you want refrigeration, you have to store natural ice. So we are not very old than the computer age. Little more old there. Okay, old. So you can see here harvesting of natural ice. Various pictures are many pictures are available. I picked one. And there are a lot of export-import business at that time. Export-import of natural ice. Just like granite, present day granite stones, they cut and export. Same way they are cutting the ice from natural ice, and you can see from 1850 it's going up and then came down. Drastically, it's become zero. So this particular graph is from Norwegian. Britain, Norwegian export-import of ice. You can see it goes up, and in about 1900 it is a peak and then die down because of artificial cooling invented. Okay? You see, India is not exception. India also brought ice. Chennai is not exception. Chennai also imported ice. You can see the ice house then and now Swami Vivekananda Hall, Chennai beach. This is the ice house then. We imported ice. Chennai imported ice. At that time, the ice is very expensive. You can't use it for air conditioning. Definitely, people are changing the capital for in summer. Summer is hot. They went for change this capital. Went to hills for summer. Later, artificial cooling invented. We got air conditioning system. They don't require to shift their capitals to hill centers. Okay. So, what are the consequences? That will come to later on. The cooling patterns of India, how it goes. Okay. The global cooling patterns of India, and in particular India, you can see where India stands. India is a very populous country. We have got 1.35 or 1.4 billion people. We will be crossing China soon, overtaking China soon. And ours is tropical country, hot. So, how much cooling is required in India? It is person cooling degree days. Number of persons into how much time the temperature is above, say, 20 degrees centigrade, 25 degrees centigrade, wherein you require cooling. So that parameter gives how much cooling is required. Person cooling degree days. That is a parameter. So the India's person cooling degree days is 3 times that of China. Though population is almost same, they are cooler country. Ours hotter country. So our cooling requirement is 3 times of China and 15 times that of USA. They have got less population and also little cooler. So when we develop, we require that much of cooling. So China is almost developed and they are almost saturated. US is already saturated. Their cooling extra demand comes for replacement of systems. And maybe a little bit more, they may require more cooling. But they are already on the S curve, top of the S curve. Whereas India is bottom of the S curve and it will keep developing. And then when we develop, our cooling demand will be almost equal to the rest of the world. Okay. So, how to mitigate the global warming? Because all of us know, I will not go into detail now, global warming. We have conducted what's COP21. The Paris Climate Accord 2015. And India ratified it on Gandhi Jayanti Day on 2016. And now we also support COP26, recently held in England. We also signatories for Montreal Protocol and Kigali Amendment for the Montreal Protocol. Present condition of India is that we have got less than 20% of the building that would be in 2030. In another 8 years, we will have so many air conditioned buildings, malls, houses, office, hospitals. More buildings will come as we develop. Present AC penetration in India is hardly 5 to 6%. And we are going rapidly, 20% year on year. So in another, in the coming years, 10, 20 years, our AC demand will go very significantly, exponential. Okay. So that is the requirement of cooling. You can see this here. This is India, predicted by IEA, International Energy Agency, after a lot of studies. And India, you can see the present we are here, 75 terawatt hour. And in next 2050, we will be requiring 1350, that is 18 times energy, only energy for only cooling. Only for air conditioning, cooling requirement. What is the energy, extra energy required? 18 times increase. Okay. So as we develop, we require more energy. This is only for cooling. Okay. Only for cooling, not other things. Only for cooling. And here you can see what is the power generation capacity required. Presently, only for cooling, we have got 40 gigawatt, and we require 21 times power requirement. It will increase by 2050. That is predicted by International Energy Agency. What does it mean? Capital investment for installing power plant. It will become 80 lakh crores at the present rate. And that is equal to 50% of the current GDP. Okay, of course, we don't put all in 1 year. It is gradually we're putting, but this much investment should go into power sector only to cater for the cooling requirement. So energy demands are increasing. Global, India is contributing much to that because India is developing stage. We need energy to develop. Those developed countries used all the energies and they developed already, but we need this anyway. So you can see the primary energy concerns. Basically, it is coal, oil, and gas. Remaining a little bit, of course, they may, as you project for the coming years, this non-conventional source of renewal may get more, but present you can see this major is coal, oil, and natural gas. What is the consequence? If you keep increasing, what is the consequence? Present itself, you can see the carbon dioxide in the atmosphere is increasing. This is not because of using carbon dioxide as a refrigerant, it's only minuscule, hardly matters. It is because of release of carbon dioxide to the atmosphere by energy or power generating companies. If you burn coal, carbon dioxide is getting released. What is the carbon dioxide footprint per kilowatt hour? Large by coal. So because of the energy power generation by burning fossil fuels, you see the carbon dioxide is increasing. Now it's already crossed 400, almost 420 now, ppm. It is increasing about 3 ppm a year. Okay, fine. It is for the people perspective, they can survive, no problem. For increasing carbon dioxide to 400 level in the air conditioned room, we normally maintain 600 ppm, 700 ppm. Nothing will happen. No problem for the well-being of the people. But consequence is ambient temperature increase. Carbon dioxide is a global warming gas. It is it absorbs re-radiated waves, long wave radiation. So heat, it absorbs heat. Okay, so ambient temperature increases, and the whole idea is to restrict the increase by only up to only 1.5 degrees centigrade anyway. Now, because of increase in ambient temperature, average temperature, Arctic sea level, the Arctic ice is melting. Now, see, Arctic ice is melting, and it is coming down. The ice levels are coming down. Sea levels are increasing, and it is increased just about 20 centimeters, 0.2 meters in the last 150 years. It's all measured. Nobody can dispute this. Sea level has increased 20 centimeters in the last 150 years. It looks very small. But if we go on doing in another 100 years, another 20 centimeters, then definitely all the coastal cities will get submerged or flooding, and they can't live as they live today. So definitely there will be flooding. Then when it rains, water won't get drained. Some of the places can get submerged, so and so. Okay. Now, what are the apprehensions now? The apprehensions are, one is rising sea level. That's really a problem. Though it rises very slowly, in another 150 years, then definitely there will be. Right now, there's a problem of flooding. You can see in Bombay when it rains heavily and high tide, water won't go to sea in the flooding. Okay. So, then abnormal weather patterns. You can see now, every day you can see the news. Half of the Pakistan is submerged now. There is heavy rain in Kerala. Now in Bangkok city is getting submerged. You can see abnormal weather patterns, hot, cold, and floods, droughts, cyclones. Abnormal. Okay. Which is nothing not unheard. Previously, in the Bay of Bengal, we had only 2 cyclones. Now it's 4, 5, 6 cyclones. Like that, it happens. Then environmental pollution. Okay. So depleting energy sources is no more valid. We will not be able to burn all the fuels which we got. We have to see that all the coals will not be burned. All the fuels will not be burned. We have to go for renewable solar. So depleting energy sources is no more valid. Solution is efficient carbon dioxide technology. Now you can see now, I'll go little fast. You see what happened in 2015 COP21 mission innovation. All the people came together, and now we bound ourselves that the carbon dioxide concentration will not go much beyond, such that we restrict the increase in ambient temperature, overall temperature, to 1.5, not more than that, compared to pre-industrial era. So we know what happened in the intervening period in US. This is started by the then President Obama, and then before 5 years or 4 years more. Now again, President Biden has come back, and immediately first thing he came and did is sign an executive order to rejoin the US into the Paris Climate Agreement. This is the news at that time. First thing he did, came back. In the intervening period, see, when the big brother is not supporting, everything will come to halt. So it's not happened. Now again, people are talking all these things, and now recently we had COP26 in Glasgow, United Kingdom, and again, people are talking, and whole idea is to restrict the temperature rise to only 1.5 degrees Celsius compared to pre-industrial levels. That is the target. For that, to achieve that, we should not use all our coal. We should not use all our oil. Okay. Then if you burn all these things, carbon dioxide will go up and the temperature will go up. This is the coming to the refrigerant selection criteria. All of us know thermodynamic properties, basically system COP. We know pressure ratio, latent heat, all these things, viscosity. I'll not go into detail. Okay. Then coming to environmental safety, ODP, nobody is talking about that because it's already addressed. Montreal Protocol is addressed. So no ODP, ozone depleting chemicals are released now. It's already capped and done and dusted. But global warming potential is there. We have to look into TEWI, the total equivalent warming impact. Both GWP and COP, both will come together. That is toxicity and flammability. Only carbon dioxide is the A1, non-toxic, non-flammable. That is the carbon dioxide. It is, of course, it's a greenhouse gas, but by volume. Its greenhouse effect is only one compared to the synthetic refrigerant of thousands, only one. So from refrigerant point of view, carbon dioxide is very good, but from energy point of view, if you release in volume, kgs and kgs and kgs, or tons and tons and tons for every kilowatt hour power generated. So then the atmosphere gets flooded. ppm raised from 300 to already 420. So it goes ppm every year. That is the problem, not by refrigerant. Chemical stability, the refrigerant should not be very stable. It should break down as you release to the atmosphere. In olden days, we say chemical stability is very good. These R12 or 11 are told that they are very stable, very good. No, they should break down when it is released to the atmosphere. That is the best thing. Inside, once they're inside, it will be stable. When outside, it should break down. Economics, okay, cost, ease of handling, and lubricant compatibility. So this gives a TEWI effect. the refrigerants used in the system has got two. One is if you release that, what will happen? What is the effect? That is direct effect. Indirect effect is on its lifetime, it uses electric power. Where it will come from? It may come from coal burning or anything. So what is the effect of that? That is indirect. Indirect is by consuming power. So one has to have put together what is the combined effect. You can see refrigerant use of refrigerants. We can see the all this have gone now. Hydrocarbon has gone in between and it's came back. Now this is introduced. Unsaturated hydrofluorocarbons or HFOs are introduced now for this one, HFCs. They are introduced, but you can see a lot of problem with the HFOs. They are kept in the back burner, but they are introduced. It becomes flammable. A lot of problems with that. You can see it becomes a highly toxic gas when it is comes into contact with hot surface. When it burns, let's say the automobile is going through a big tunnel and then something happens, poisonous gas will be released. And this is another one, long range. This HFOs break and they make trifluoroacetic acid, TFAs, as a degradation product. When it degrades, makes and it will absorb the water and it will never come out. We can't do anything. It's done. Now it is there. We can't do anything. It can't be removed. And this is it. So this is a big problem. How to avoid, we don't know, but people still go ahead with the HFOs. The maximum allowable concentration of 1, 2, 3, 4 YF, the workplace only 200 ppm, very less. So you can see CFCs have gone. Okay. SCFCs are going, still they're going. HFCs are scheduled to go, at least phase down, scheduled to go. And unsaturated HFCs, that is HFOs 1, 2, 3, 4 YF, etc., are introduced now as a replacement, but they have to go one day. Coming to the comparing to the properties of refrigerants, you can see water. This is natural refrigerants. This is synthetic. You can see into, all not good. Now we see water. We need global warming potential of water because if the water vapor is not there in the atmosphere, it's an equilibrium already. Not there, our global temperature would have been minus 18 degrees centigrade, uninhabitable. So we need that. It's already steady state. No problem. It should be there. And carbon dioxide is high pressure. It's good. We have to convert it. It's good. So you can see in here carbon dioxide. Everything is GT. So we have started with natural refrigerant long back. At that time, you use whatever works. The health issues or safety issues are not considered. Then safety issues came, then ozone depletion, then global warming. Then you have always come in a full circle. Why you can have a frog leaping to natural refrigerant again? Okay. That is the introduction. That is, we need to go back to natural refrigerant, in particular to carbon dioxide. Can we go frog leap, go straight without HFOs? Okay. Coming to the how we can use carbon dioxide. For that, you need a little bit of fundamentals of Carnot cycles. You must be knowing Carnot cycle, 1, 2, 3, 4, Carnot refrigerant cycle. Here. Adiabatic, isentropic compression, isothermal compression, isentropic expansion, isothermal expansion. So this will absorb heat. We know Q is equal to TdS. Heat rejected is area under 2, 3. Then heat absorbed is area under 4, 1. we know the cycle for a cyclic system, Q is equal to W. And so this is the work done. We know we can use some fundamental equation, isotropic work, isothermal work from the thermodynamics, and ultimately you get this is the work done, the blue is the work done, and the green is heat absorbed in the reference system. So we can say COP is heat absorbed by work done, heat absorbed divided by work done is equal to T1 divided by T2 minus T1, and Carnot cycle is independent of the working fluid. Okay, we don't know, it is only temperature. This gives the is a reversible maximum CO2. Now use this Carnot CO2, reverse Carnot cycle or Carnot reference cycle, which works with gas, to develop our system systematically. So this is the, because we can't have 4-1 and 2-1. It requires a lot of time. No? It's a very slow process. You can't build a system. So what we do is you convert 2-3 and 4-1 into the condensation and two-phase process, and you have boiling process. Fairly fast. No? So same shape is retained. So this is CRC with phase change. But here again 1-2 is not possible because wet compression is shifted to the saturation. Again 3-4 is not possible because again lubricant washing and so on so forth, difficult. So we put it into, instead of expander, with throttling. So this is standard vapor compression cycle, which mimic somewhat this, close to that. So which is a workable. Of course, we have got deviated and additional losses will be there. It's not reversible. So this is standard vapor compression cycle. Now, carbon dioxide, it's a natural refrigerant, 0 ODP, very low GWP, just 1, comparing to the HFC, 134 of 1000, 2000, 3000. Okay. So it is very less, negligible. It has got high critical pressure and low critical temperature. You can see this is the CO2 pH chart. The pressure is critical pressure is 73.7 bar, high pressure. Okay. We have to convert high pressure into advantages. When high pressure is inevitable, you try to use it to advantage. Okay. High pressure, that means high density, gas density, reduced compressor swept volume, because the compressor becomes small refrigerant lines, tube becomes very diameter less thickness is sufficient, compact and less weight. Ultimately, the whole system becomes compact and less weight compared to the conventional refrigerants. Low pressure ratio, the pressure ratio is less, high compressor efficiency, high heat transfer properties, good properties for thermic fluid properties, less viscosity, high thermal conductivity. So you've got high heat transfer rate and low specific pressure drop, because low viscosity. These are advantages, but low critical temperature. So you have to go for transcritical cycle. I'll come to that. This is a TS chart available. You can see this is the critical temperature, 31.1 degrees centigrade. What happens if you go from, because we have to operate in this range, because temperature and pressure sensitivity. What happens if it transcritical operation, when it comes from here to here, or here to here, liquid, all these things, what is that? Then you can see this phase change transfer across critical point video from Dan. You can search, of course, phase change, and Google will get it, many videos. This is one video. If you want, you can take a screenshot, or you can write down or Google, and you will get many. Okay? You can see for yourself how the phase transformation takes place when you cross critical points, critical line. So we are operating at critical lines, critical, above critical, but below critical, right? So we have to see what is the difference. This is the conventional simple VCR cycle, simple VCR cycle. Now, what is transcritical? See, now transcritical means there is no condense. This here 2, 3, desuperating and condensing. Here no such things. Whole thing is above. Above. Okay. That means it doesn't condense. So condenser becomes gas cooler. Okay. Then 3, 4, you can see here 3 above the critical line. That means it is a gaseous. As you throttle it, as it flows through the capillary tube or whatever it is, it becomes, you see, 100% liquid now. Then two-phase region. So there's a transcritical from supercritical to subcritical. It goes from 3 to 4. That is the difference. Because of this, no, because of this high pressure gas, and you throttle it, all your energy is lost, exergy is lost, energy is lost. So as the ambient temperature comes down, this line comes down. You come into subcritical. So at lower ambient temperature, you can see carbon dioxide does better, COP is better than the conventional refrigerant. As ambient temperature increases, you see the COP degrades very quite fast, faster than the natural refrigerant. Okay. So at high ambient temperature, carbon dioxide cannot compete in a normal way. So you have to see what we can do to improve it. So again, you can see, you can take a screenshot. Softwares are available to play around. You can just, this is simple one-stage CO2. You can just vary the pressure, vary the evaporator temperature, pressure, all these things, and you can play. You can give the COP and you can play around. You can note down or take a screenshot, or probably this video will be available to you at this 20. You can my slide 20 you can see later on also, or take a screenshot. If you this one you can get the online. You can play around, recycle and get the COP and then do your own thinking and vary one parameter and find out what is used. How to improve now? How to improve? First is cascading. If ambient temperature is 40 degrees centigrade and I want minus 30 degrees centigrade in the evaporator, so don't use carbon dioxide as a single gas. Use the carbon dioxide as the bottoming cycle, and top cycle is R717 ammonia, and ammonia will the condensation temperature is 45 degrees centigrade and it evaporates at say minus 10, picking the heat from the condenser of the CO2 at minus that temperature, and you have got here minus 35. So in that way, carbon dioxide is restricted to subcritical operation. Okay, so your ammonia condenser is minus 10, and this condenser, CO2 condenser, minus 5. So 5 degrees centigrade difference to heat transfer. So your CO2 system will ask in subcritical, of course, ammonia is subcritical. So your efficiency will improve. So that is one way of doing, and probably this you can I read myself. And this is various. I think Professor Ram Gopal give natural circulation loop. Okay. The other method is to have dedicated mechanical subcooling. So here you have got 40 degrees centigrade of the gas cooler, and you can cool to 30 degrees centigrade by using separate system. And this cooling is very simple, easy, because efficiency is more, COP is more, because you're cooling almost near to ambient temperature. But when you throttle, you will get the same amount of cooling at much lower temperature. You will magnify it. By second law efficiency, you will improve substantially. So this is a simple trick you can use to improve the efficiency. Subcooling at higher temperature, but it will give the whole amount of cooling at whatever you cool here, it will give exact same cooling extra here at lower temperature without any further work. So that is the good effect. Thermodynamic second law efficiency improves very much. You can use various aspects. Here is also you can use with integrated mechanics subcooler. You can see you can tap some refrigerant throttle and subcooled remaining. So here you can see this comes here, the heat. This is cooled by using this. Heat transfer takes place from this. So this is inbuilt, in-house cooling by carbon dioxide itself. This also improves the efficiency. You can use evaporative cooling. All of us know evaporative cooler, whether to use evaporative cooler full or half or 1/3, because this is very high temperature, already 90 degrees centigrade. What is the use of cooling air from say 40 to 30? No much effect. But fag end of the gas cooler, you will get benefit. You can see here the COP improvement takes place 17% for the 30% pre-cooling, whereas 27% for half. Of course, you'll get better, but at the expense of lot of water. Water consumption is much higher. You have to optimize that also. Internal heat exchange, you can see here the internal heat exchange is already, so you can transfer heat from 3 to 4 for the to the gas coming out of the evaporator before the compressor inlet. So this is the internal heat exchange. This the carbon dioxide is one thing which will enhance. Not all refrigerant. Most of the cases in CO2 system it will increase. So by having this, we can increase. So it will give, not always, most of the case times COP improvement will be there. Evaporative flooding is possible. By evaporative flooding, you can have more efficiency for the evaporator and whole system. Compressor safety, the compressor will never get the liquid droplets, and increase the discharge temperature. If you come to this way, in discharge temperature will increase for the heat pumps or heating applications better. So 4 aspects of this. COP improvement may not be always. Pressure optimization, you can see the conventional refrigerants, it is in the subcritical region, 2-phase, either pressure or temperature. Only one is independent, other is dependent. Once you fix the pressure, temperature condensation is fixed. But here we are operating above critical bucket, both pressure and temperature independent. You can play around. You can find out the for the same temperature, ambient temperature or gas cooler exit temperature, I can find what is the optimum pressure. You can see from here to here, you can go. Some increase in power is required, but cooling benefit is large. Then further increase pressure, same amount of work input is required, increasing, but benefit is less. So obviously it's optimum. You can see here as the gas cooler ambient temperature, gas cooler increases, your pressure will increase, optimum pressure will increase. This is one way. These are low-lying fruits. These low-lying fruits, you can use this technique to optimize. Other thing is expander. You can see this simple system. This is only expander here. I'll skip all these things. Expander. Okay. So expander is you can get the power back into the compressor, and the exit of the compressor cool. So it has got 2 benefits. One, work input will be less. Second is more cooling. So you get 2 benefits of having expander. But when expander is there, then the internal heat exchange will not give, because you can see here with this both together you can go only 2.98. When you remove internal heat exchange, COP increase further. So you can't say that IHS always improve the efficiency. You can't say, but in general, yes. You can see from here the simple system to then also you can see the expander with the double stage compressor with intercooler. This is another method. 2-stage compression with intercooler, that also increases the COP. Compared to this and this, you can see this almost 40% increase in COP, 2.5 to 3.5. 1 in 2.5. There is 40% increase from here to here. That's remarkable. We have to use all the techniques. Then evaporative flooding is possible, and splitting of the evaporator. So that also increases the COP. So now, you see, we can't use the expander because we're still in the developing stage. So expander is not available in the market. So what should be done? Okay. Expander is not possible. We know what are the inefficiencies in the system. You have to identify. you can see one is the throttling loss. Of course, we talked about expander, that throttling loss will not be there, but very difficult to use the expander. Not possible. So throttling loss, you can compare R134 red. Cycle is 1, 2, 3, 4. Cycle. Compared to CO2, you can see CO2 1, 2, 3, 4. Green line. Difference is the addition losses. You can see throttling loss is much extra and increase in heat rejection. These are the addition losses compared to R134A conventional. Okay. Because of this already explained. So you can use ejectors. You will see that and utilize the heat efficiently. This ejector system development. This is the transcritical system. This is one improvement to pressure you can make, throttle to intermediate pressure, separate the gas. Okay. Of course, thermodynamically both will be same, no advantage thermodynamically. Now instead of that, you can send the parallel compression. Instead of throttling and coming back, you can directly compress. So it's a parallel compression, it improves the efficiency. Now we will go for ejector system instead of that. These both are same now. Okay. Now I'll remove that. I'll remove this throttling, put ejector, then ejector compresses this free without it, because using this energy available in the high pressure gas, it compresses. So this is the cycle. Obviously, one compressor is not required, and obviously it is because you have recovered this energy available in high pressure gas to compress this gas. That is the ejector system. Obviously, there will be imbalance will be there. I can't exactly match. Then we will need a small compressor. We will need to purchase. So this is the ejector system, and you can see the ejector system. 3 high pressure gas expanded and supersonic comes, okay, and it sucks the low pressure gas, mixes and recovers the velocity into pressure and pressure. So we have got 2 parameters: entrainment ratio and ejector efficiency. Okay. How it works, you can see this pressure, motive steam, high pressure gas, pressure decreases and velocity increases, pressure to kinetic, and their mixture and pressure regain takes place at the expense of velocity. You can see, as a layman, you can see this pictorial. So without flocking, this bird takes this food, and without flocking, it goes to higher level. Pressure, height, convert to velocity, flux, and goes to a certain height with this load. So this is the single ejector. Yeah, pack, ejector pack. You can see the size. Of course, this will be a little bigger. This is single ejector, and ejector efficiency you can get 0.1 to 0.35. You can't have 1 because there's a mixing losses. Though there's no thermodynamic limit, but limited to this. Entrainment ratio 0 to 1 depending upon the pressure lift and pressure ratio. You can see this. You can compare the R134A because direct, indirect. The R134YF, that is HFO and carbon dioxide. Carbon dioxide looks not competing with this 1, 2, 3, but with the ejectors you can see it will be better than 134A also. Now we identified loss, throttling loss, use ejectors, 1 to about 0.35 or 35% you can recover and use it. As long as the expanders are not developed fully, we can't use it. Ejectors are very simple. We can use it. There's no moving parts now. But what heat rejection loss, what you can do? So when heat rejection loss is inevitable, use it for heating something useful if possible. In other words, you can use the system only where you need that heat. The hot stream, that is CO2 cooling, say 95 to 30 degrees centigrade, it has to cool, and cold stream. Now we are using abundant air or water. At this temperature, it comes out. So whole exergy is lost. Nothing. So then you can't use this system, or your system efficiency will be less. So now instead of that, you heat it to some extent and use this heat. So partially recovered, and it's still better. Exergy of hot gases recovered still better, and this is 100% to match how the carbon dioxide cools. You heat parallelly something matching, then no loss, absolutely no loss. So whether you can achieve that or near to that, utilize the heat efficiently. So once flow through water, heat and use type is a perfect application for CO2 system. You can see the hot water, the CO2 gets cooled, and parallelly we get counter current. You heat the water as much as possible, as much close to this. 100% not possible. You have a pinch point here, some problems, but still you can recover the heat. You can heat the water up to 90, 80, 90 near boiling point temperature. Okay. So possible applications. CO2 system extensively used in Europe, both subcritical and transcritical modes. In India, the operation is mostly transcritical mode because of high temperature. All performance improvement technique must be put in place on case-to-case basis for maximum performance. Options: gas cooler pressure optimization, ejector technology, multi-staging, intercooling, IHX when required, evaporative cooling of gas cooler, cascading. Whatever explained, it may not be possible all to be used, or whatever possible. Multi-staging we can use. Inherently, it allows intercooling, and once you multi-staging, many temperatures are possible. Low temperature, medium temperature, air conditioning possible, and also, you can heat. So it's ideal for supermarkets and hotels, hospitals, where both cooling is required and heating required, or cooling at many temperatures. Low temperatures -30, medium temperatures -10, AC +5, 10. All temperature of cooling and heating required, and you can use it. Application in India, many segments are there where you can use, because which requires both heating and cooling, or multiple temperature of cooling. All these things can be accommodated by CO2 system. Again, a water heating pump is a perfect application. You can see we are using it for a centralized kitchen. Actually, here, we get 1/3 of diesel saving for heating. For cooking, you need to preheat the water, then boil. So we take care of the preheating of the water from 25 degrees centigrade to 90 degrees centigrade. That accounts for 1/3 of the fuel. So great saving. Okay. Overall COP becomes 6.25, including heating. And even here we need this IHX. This IHX is required, which will boost this temperature. Without IHX, temperature will be less. It's not sufficient. We have to boost it. Of course, we need IHX to safeguard the compressor, to boost the discharge temperature, and of course, if possible, increase the COP and so on. Dairy application, you can see pasteurization of milk. It requires heating and quenching, cooling quickly. So at present we use ammonia chiller with the brain for cooling, and boiler, furnace oil fired boiler. So we can use this system, this carbon dioxide system, and we can see all these things can be accommodated with heating, both heating and we can have 2 evaporators, one low temperature evaporator for butter storing and things like that. Heating also used for cleaning purposes. So milk dairy is another application. Supermarket, you can see, of course, present day in India supermarket, we don't require much LT and MT, only air conditioning, and heating also may not be much. But in future, we also copying the Western countries. Definitely, nobody will go and buy fish from the market. They'll go for the supermarket only. They'll not go for the slaughterhouse. They'll go for supermarket only. So definitely, we will record all the applications. You see, AC temperature, medium temperature -10 or -5, and the low temperature -30, and heating also for cleaning and all. So this is the requirement. Definitely, if this is proportion is required, then carbon dioxide can be used. Future trends, definitely CO2 is a preferred alternative for most of the installations, hotel, hospital, water plant, supermarket, etc. Can adopt CO2 reference system. It can be successful phase-in straight away without going in for HFOs. We can leave frog leaf and go directly there. Summary: tremendous development in CO2 technology. Energy efficient CO2 systems have been introduced in the market, not in India, in different countries. CO2 system enable flooded evaporators, flood efficiency more. LT, MT, and HVAC is possible. Ejector technology offer high system performance because we can recover 35% of the energy available in the high pressure gas, even at high ambient temperature. High temperature heating is also possible, and simultaneous heating and cooling is an apt application for centralized kitchens, hotels, hospitals. CO2 is only the A1 refrigeration candidate. OEMs with clear strategy, they should jump on it. They'll become market leaders. They can take the market share in advance. Okay, frog leaping is intended. We have to work on that. Authorities have to support. The government support may be required to push CO2, so that because the other refrigerant, the lobby is pushing, the carbon dioxide got no backing. So there should be some backup from the government. Knowledge transfer and training is the key, because this carbon dioxide is operates 100 high pressure, and how to weld, safety training, trained personnel is required, and training is essential. Tremendous scope where both cooling and high temperature heatings are required. Non-technical barriers such as awareness, knowledge barrier, social organization, and legislative barrier have to be crossed. Thank you very much for your attention. I want to acknowledge the support given by Dr. Simarpreet Singh. PDF is no more, not now, earlier. He is the person who started this SPARC project, the proposal and everything. Professor Armin Hafner, my colleague, I have taken some of the slides from him also. Mr. Dasi Koti, he was my MS scholar, I took some slides. Mr. Guru Chetan, PhD scholar, taken my slide, and also Dr. S. Sivakumar Reddy. Thank you very much. Thank you.
Thank you, sir.
Thank you.
Thank you. So, thank you for emphasizing on CO2 refrigeration system applications as well as possible improvements. So this will give the participants a broad overview of the CO2 refrigeration systems. Now I would like to request all the participants can ask any questions if you want. Either you can post in the chat box or you can raise your hand. I will unmute you and you can ask the questions.
Can we shift it to, okay, fine.
What's it?
Now it's 5 o'clock now.
Okay.
5 o'clock now. We are little lagging. Okay. So we can take the question at the end also, no problem. Or they can write to us. My email is there.
Yes. Yes.
Or write to anybody. Or at the end, 7 o'clock also, we can ask the questions.
Yes. So participants, we can have question and answer session at the end of these sessions. Now, we will move on to the next session. So next session is clean cooling technologies for India. So by Professor Armin Hafner. So Professor Armin Hafner received his PhD degree in Energy and Process Engineering from Norwegian University of Science and Technology, NTNU. He is the professor with Refrigeration Engineering and Technology at NTNU, Norway. His research addresses the utilization of natural refrigerants such as CO2 for various applications such as refrigeration, air conditioning and heat pump system design and life cycle climate performance assessment. His research has led to more than 150 international and national publications and numerous presentations in international and national meetings and conferences. So now, Professor Armin Hafner, unfortunately, he is traveling, so he has shared his video lecture. So now I will share his video lecture. Oh, I think video is visible to everyone.
Yeah, actually, no video is visible, but the audio is not coming.
Audio is not coming.
Yeah, still
No?
no audio is not coming. So,
Shiva, you can take help from others. If somebody
Yes,
knows, you can have.
it's not visible.
Very warm welcome to the Clean Cooling Technologies for India, presented by Armin Hafner. I am professor in refrigeration technology at NTNU, Trondheim, Norway. I'm very glad to be part of this SPARC event, and I'm looking forward to your questions afterwards. First of all, I would like to introduce where we are from and where Trondheim is in Norway. As you can see, Norway is a very long country, but we are in the middle part of Norway, and we are just below the polar circle. Trondheim is more or less on the same height of Anchorage, Alaska. So let's see. We are a large university while Trondheim is the capital, the technology capital of Norway. We have about 45,000 students and a staff of nearly 8,000 at NTNU, while our partners at SINTEF have a staff of around 2.2 thousand. Our turnover is about 1 billion euro, and we are a scientific and technology cluster and an innovation team of a large strategic importance to the Norwegian society. And on the left hand side you see a picture of our campus in the city of Trondheim. And your contribution actually is very essential, because clean energy is for a future with a peaceful and a sustainable society. That's today's largest challenge. And clean energy is really required to provide for essential human needs like food, housing, transportation, clothing, health and recreation, to live a good life on this planet. And this is a responsibility for all of us, and we can help. That's why the content for today will be a short introduction on clean cooling technology and the historical background, and why clean cooling is a necessity today and how we get there. What kind of applicable and energy efficient working fluids do we have? The focus will be on CO2, but I will show you why this is smart to use and when it is smart to use. I will show you some system architectures for various refrigeration and heat pump units, and I will give examples from industrial installations. At the end there will be a short summary, and I will also focus a bit on further work and the possibilities we do have in the different projects where we have educational units and demonstration sites. So what are the drivers when we look back? What were the drivers for the introduction of mechanical refrigeration more than 100 years ago? Well, it was the factor that pushed the development of this was actually artificial ice production, which was a huge thing more than 100 years ago. And as you can see on this advertisement, there have been a fight at that time also between the artificial production and the natural ice production. Of course, everything started with natural ice. As you can see on this picture, more than 150 years ago, ice that was related to refrigeration. And for example, in Norway, we exported 300,000 tons of ice towards Great Britain, a little bit less to Germany, France and other places, but a huge amount of ice was exported between 1860 and 1915. It all came down to close to zero because artificial ice was then produced, as I will show you in a minute. Because these kind of machines, as we can see an advertisement from 1922, they kind of took over the production of ice, so everybody could access ice all over the world. And the second was brewing of beer all year long. That was the intention, and that was the kind of giving the possibility for the beer brewers to do this beer brewing all year long. And the person who made it happen was Carl von Linde, because he developed mechanical refrigeration technologies, and within a very few years he sold nearly 750 large ammonia refrigeration systems all across Europe, and some are even exported. So the third one was the transport of meat. By that time these kind of ships came from South America even to Asia and to Europe, transporting a lot of meat. And as you can see here in the bottom, a lot of meat is transported in this refrigerated carrier, while the CO2 systems have been, as you can see on the upper left here, you see the CO2 refrigeration system was applied to keep this product frozen. And here we can see also another view of a machine room with two CO2 refrigeration units on both sides. So the refrigerant journey until today, we have seen that everything started with ammonia and CO2, and yes, until the 1930s the mainly natural working fluids have been applied. However, in the 1930s until lately there was a massive lobbying and an introduction of safe synthetic working fluids, mainly the CFCs and HCFCs, which are still used in some parts of the world. But due to the Montreal Protocol in 1987, there is a strong focus to eliminate the usage of CFCs all over the world. And it was remarkable that this international protocol was ratified within 2 years only, which was really exceptional. It has never happened before, and hopefully it may happen again, but it was a very uniform introduction of this protocol all over the world. It triggered the introduction of the HFCs, which we will come back to, but it also initiated the revival of CO2 as a working fluid by Gustav Lorentzen and other natural working fluids. So 10 years later, the Kyoto Protocol was supposed to deal with the global warming potential. It took 7 years to ratify. However, US didn't join. China and India were exempted from reduction commitments, so there was not much happening due to the Kyoto Protocol. In 2006, the European F-gas Directive came up, which was updated in 2014, and it is phased down steps based on GWP for the working fluids. And the Montreal Protocol, there came a Paris Agreement, and we had the 2016 Kigali Amendment to the Montreal Protocol, where also India has committed to reduce the greenhouse gas emission of the working fluids. And again, we see now a massive lobbying that pushes the introduction of ultra-low global warming potential HFCs. And the question is this F-gas journey to the best for society and the environment? Let's have a look on that. And first of that, let's have a look what is the state of the art of these synthetic refrigerants. The use of these F-gases in the past decades has a severe impact on humans and the environment. We can see that the ozone depletion could be returned or reversed because of the Montreal Protocol. We are glad for that. However, we can see that the global warming is still a big issue, and it's related to the working fluids. A lot obviously is related to the working fluids. However, lately we also have understood that we get poisonous decomposition products from these synthetic refrigerants, and these PFAS are so-called, they are per and polyfluorinated alkyl substances, and we know them also as forever chemicals. So these are not chemicals which occur naturally on this planet. And we have an acidification of our water, our drinking water, by TFA, which is a PFAS. So what is then the question is, what are real sustainable working fluids? So we are on a path to that, and I try to help you to understand how we get there. What are sustainable working fluids? McLinder from NIST in the US, he intensively screened to identify these fluids. He used the PubChem database, and he analyzed more than 60 million chemical combinations. He did some simple cycle calculations to investigate the performance on these fluids related to a system for a COP and the volumetric capacity. That what he screened on 60 million combinations. And the final result was a list of 27 fluids, which you can find in his publication. And these compromises hydrocarbons, some HFCs, some HFOs, short life HFCs actually, CO2, ammonia, and a total of 5 components with oxygen, nitrogen, or sulfur. So the first and very important conclusions: there are no fundamental new classes of chemicals available for the use in vapor compression systems. So there is nothing else. You cannot continue and hope there is something coming up. Second conclusion, which is also very important for existing systems, because drop-in replacement refrigerants require no change to equipment design is appealing. However, the properties of these fluids will generally be different than the fluid they are replacing. That is very important to understand, and recognizing and adapting to these differences will be required. So there is no chance to utilize an old system and believe you can just drop in a fluid and it is back to run, because most likely these new fluids will be flammable. The old system is not designed to be operating with a flammable fluid, and that has a severe safety impact. So, as I described and before, you can see this is our toolbox. Everybody recognize this toolbox, and we can see that there are only 8 elements. They're really suitable for our molecules for the refrigeration. However, the more you go down, the more toxic it becomes. The more to the left, the more flammable. So there is a balance between low global warming potential and flammability. The lower the GWP, the more flammable the fluid, except CO2, for example, but we will come back to that. So what are sustainable working fluids? If you look to the upper left, this is where we have been for decades. I mean, the methane-based fluids like R12, R22 and 32 and so on. This was our toolbox for the last decades. And now we are going to the propene-based fluids, where we have 1270 as the hydrocarbon on the lower left. If we replace all the H atoms, all these, with chlorine, we are up in there, but that we don't want, because that means global warming. Not only global warming, but also ozone depleting. And if we replace every atom with the F molecule, we will be on the R1216, a hexafluoropropylene. So, as I said, here up we don't want to add any chlorine, so there is ozone depletion. These are not any alternatives. And what are the challenges with these ultra low GWP values based on still having fluorine atoms on the propene molecule? Well, the 1, 2, 3, 4 YF, as I just said, it transforms mainly to HF and TFA. So that is something we don't want. And it will be very soon restricted. I will come back to that. The SETI is also transforming a little bit to TFA. However, it also, there is a high likelihood that it transfers part of it into R23, which has a very high global warming potential. That is not good. So there are more experiments on the way, but this, from the precaution point of view, we should be careful using this fluid. And the definition of global warming potential is very weak, because it should be a LCA based global warming potential value. They are needed because it would include the manufacturing, but also the decomposition, which is not the case today. It is a very weak definition on a 100 years perspective, and it's not at all taking into account the environmental impact of producing and decomposing this fluid. So this is how I believe, this is how I think we are looking on GWP values, and we should do more careful investigation. So this is another way to illustrate it, where we are. We have the global warming potential of R23 is the skyrocketing. We have ODP, mean ozone depletion potential of in this direction, and the only way, the only place where we can work is actually down to the left in Origo, where we have our natural working fluids, because they have neither global warming potential nor do they deplete the ozone layer. And from the precautionary principle, we should stop use F gases as soon as possible, immediately. And we have in Europe the F-gas regulation, and the Kigali Amendment goes in the same direction. But there is the PFAS restriction sailing up on the horizon. And the F-gas regulation is fine. However, it does not care, as I just mentioned, about the real environmental impact of the refrigerants, because it just takes into account what is in the bottle, but not how it was produced and what happens if the bottle is released to the ambient. However, the F-gas regulation supports the fluid of low GWP, like the natural working fluid, but the boundary conditions, how this is defined on the 100 years perspective and so on, is very discussable. On the other hand, we have this universal PFAS restriction by EU, which will regulate and initiate the final phase out of F-gases. Those with high global warming potential will be taken out due to the F-gas regulation, while those who have this challenging with the TFA decomposition will be covered by the PFAS restriction. if you want to hear more about this, I would recommend you to visit this YouTube, and you can easily find a nice presentation by the Norwegian Environmental Agency, which is taking care of this part currently, together with Sweden and Germany and Denmark. And even I would recommend you to have a look into this just released report from Atmosphere on the rising threat of HFOs and TFA to health and environment. You find it on r744.com. All this in mind, we see that we should focus. And why should we focus only on natural working fluids? The answer is really simple. Because you and your customers, you will face no risk to invest into technologies being on the phase-out agenda in the future. And there, as I just showed you on the past slide, there is a phase-out agenda. It's the F-gas, it's the Kigali Amendment of the Montreal Protocol, but also the PFAS restriction in EU. So this is the end of the F-gases, and that's why we should focus on natural fluids and invest only in those, because that's a safe and sustainable investment, and it's real clean cooling, not greenwashing or anything. So, what are the most relevant natural working fluids? There are more than these three, but these are the most important to my mind, what I would highlight. And today I will focus mostly on carbon dioxide, which is also called R744. It can be utilized very well in hot water heat pumps, as we will see later. It can be also a commercial low temperature industrial refrigeration, and we can even produce heat pump water chillers and some other transport refrigeration, as I will show you. Today I will not focus too much on ammonia, but ammonia has been utilized since the early days of refrigeration. Remember my introduction where Carl von Linde made 750 large ammonia systems already 150 years ago. That is remarkable, and this fluid has been in service since the start of mechanical refrigeration. It is utilized in industrial refrigeration and heat pumps, and it has its place all over the globe. We have also hydrocarbons, propane, butane and others, and we can use them in residential AC split units, as we have in India on Godrej and other brands. All the light commercial refrigeration, mainly across the world, are done with butane. And we have the home appliances, fridges and freezers, also done with butane, and the light commercial mainly with propane. And of course we can do high temperature heat pumps, maybe with even larger chains of hydrocarbons, with a very high performance on high temperature heat pumps, which is not the topic of today, but it is a very interesting topic too. So when we look at the properties of the working fluids, focusing a little bit on CO2, R22, which you are very familiar with, and just as a reference also ammonia. But we can see that the saturation pressure at different saturation temperatures is much higher for CO2 compared to R22 or ammonia. This is significantly higher, which has its benefits because it, as I will show later, the pressure ratios are lower and the density of the fluid is higher, so we can have much smaller pipes compared to other fluids. When it comes to the temperature difference at the given pressure drop, we see also the opposite, that the value for 1 Kelvin, for 1 bar temperature, one bar pressure difference, the delta T in ammonia or R22 are quite high at these very low temperatures. While for CO2 you can see at these low temperatures 1 bar pressure drop is only 3 Kelvin temperature difference, which is very good if you want to have a uniform temperature at your evaporators. And the further up we come, the smaller this delta T becomes, which is a huge benefit. When we look at the pressure ratio versus the condensing temperature, we can see that the pressure ratio for a CO2 unit is much smaller compared to R22, which is even higher than for ammonia. And as we know, the pressure ratio has a major impact on the isentropic efficiency or the compressor efficiency. So we can achieve a very high isentropic compressor efficiency at a relatively low pressure ratio, which is the case for CO2 in most of the applications we are talking about. So if we then look at CO2 as a working fluid, there are advantages and there are challenges. Let's have a look on the advantages. When we look at the high refrigerant density, this means we have a reduced compressor swept volume and small refrigerant lines, which is super good if you want to do installations. Small lines means less material, more space for insulation and so on. We can also notice that we have a relatively high compressor efficiency compared to standard fluids because we have a lower pressure ratio. And in addition, we have high heat transfer and low specific pressure drop, so we can really tune our heat exchangers to the utmost. Of course, there are challenges, and one challenge you can see on this, the increase in heat rejection loss compared to a traditional condensing cycle. However, we can use this increase in heat rejection loss in the heat pump to produce high temperature water. A high temperature lift on the gas cooler is possible, and that's why it is so beneficial to utilize heat recovery whenever it is possible with the CO2 system. The next challenge or opportunity for CO2 is a relatively high or the increase in throttling loss at elevated temperatures here. So this area becomes bigger and bigger the higher the temperature. This can be utilized. This expansion work can be utilized because it is much higher compared to traditional fluids. So that's why we can, for example, utilize an ejector. So what temperature ranges are we talking about? And for CO2 applications, we can reach levels, I will show you in a minute, down to -50, not to -70, but then we need to do a cascading system, but that's not the topic of today. But we can work from -50 to plus whatever is needed, but it's very important to understand, of course, the evaporating temperature. It depends very much on the system architecture and the product. What do we want to do? And as I showed you just before, it is very interesting to have very low temperature application with CO2 because you can have a very uniform temperature across your heat exchanger, which is interesting on blast freezers or freezing tunnels and so on. And the lower the temperature, the lower the freezing time, and the duration for the storage is very important for what kind of evaporating temperature we should utilize and what kind of quality do we want. So now I would like to go into a system architecture for low temperature refrigeration units, maybe from -50 up to -20, in that range. I will show you CO2 as an evaporative secondary fluid, which is very often applied, or we can go into a system and look into a system with this cooling process, a cascade system, and then we look into a transcritical two-stage system. At the end we will see a booster system where we have two temperature levels, one for freezing and one for cooling. So when CO2 is used as the evaporative secondary fluid, we replace a typical glycol with CO2. This has a significant impact on the power consumption, on the efficiency, because we have very efficient pumping with CO2 and we have flooded evaporators. We have oil-free CO2 loop. In this loop we can pick up all the heat at the different places and very safe because there is no critical fluid near food, for example. That's very, very good. Instead of having a poisonous fluid around, where the leakage might destroy all the harvest with CO2, this is very safe. And we have a very high chiller energy efficiency, and we have a very small pump and pumping power compared to glycols. It's a bit expensive, but it is a very solid installation. And the important thing is, of course, the primary loop. It can be done with ammonia or hydrocarbons, and this is typically applied for industrial freezers, or even ice rinks are done like this. In case you have a non-continuous operation of your freezing plant, you need a cold finger to keep the CO2 at a certain pressure level to remove the heat leakage into the vessel to keep the charge inside. And this is typically done with a R290 small unit, just keeping the pressure at the level it should be, while the main systems are off. This is an example of such a system from Maicom in Japan. They have sold thousands of these units across the world, and they have reduced a lot the charge on ammonia and the power consumption compared to a traditional system with glycol circulation. This is super efficient and very compact. When we look into another configuration, we can look at the cascade system, where the secondary side again is maybe with ammonia or propane, and the first stage has now a compressor, not a pump like before. We just compress the CO2 and we condense it in the cascade heat exchanger, and the liquid tank stores the fluid, which is then kind of delivered to all the different evaporators. It's a very energy efficient process. We have a very reduced operational cost, and this kind we don't have any ammonia leakage into the place where we have the valuable food. And of course, the challenge is always that both systems must be active at the same time. The first stage is always dependent that the second stage is in operation. Again, if these parties are not in operation and this one is also stopped, we should have a cold finger to keep this pressure low in the first stage system. This is again an example of a Sabro unit. I think nowadays they go up to 1 megawatt, and you can have a temperature down to -55, which is a very interesting feature for fast freezing of products and low freezing time, for example. When we look into a conventional cooling process, also a cascade system, and then in this case we have several temperature levels in the CO2 system, which is a benefit in many times. And you see the same configuration on the left hand side, but now we have added a pump on this intermediate temperature level, and this pump is circulating CO2 at this level, maybe around -5 or -10, depending where we want to have this temperature level. So we have flooded chillers in this part, and we have the evaporator, the freezers on this part. Very compact and a robust system. And we can do a transcritical two-stage compression system also. And then this is often applied for industrial freezers, and it's very robust and developed. It's a strong competitor to ammonia systems, and it is highly recommended to utilize the heat recovery potential up here on the high pressure stage to produce, for example, 90-degree water, which is mainly also needed at these kind of plants. This system might have a reduced energy efficiency when this gas cool outlet temperature here is becoming maybe higher than 25. So that's why it's so important to look into heat recovery and find this customer who needs both the very low temperature but also process water to clean the equipment and so on, because that's the winner when you can sell a system like this. An example of such an installation on a fishing vessel I will show you here. It's a small stern trawler. They have had the capacity is normally 120 metric tons a day, and they had previously an R22 system on this ship, which you see on the left hand side, and at the same place inside the ship they implemented the CO2 system. They could increase the number of metric tons per day. Sorry, it was 30 before, and now it's 40. The freezing time was significantly lower, and the defrost was very fast when they had the plate freezers where they used this equipment. This is typically how the system looks like. You have the two-stage compression, intermediate water cooler, and you have a seawater cooled condenser, and you have this intermediate pressure vessel and the low temperature pressure vessel around -50, and the CO2 liquid pump, which delivers the CO2 to all the plate freezers. And they look typically like this, where fish is stored in this between the plates and frozen, and the vertical ones look like this. And another installation utilizing CO2 down to -53 is at CERN, where they do cool detectors at the CERN LHC, Large Hadron Collider, with CO2. And as you can see on the sketch down here to the right hand side, evaporation is at -53, and it is a two-stage process lifted up where the gas cooler rejects the heat, and on the left hand side we see two parallel installations which are maintaining the pressure down to -53 and reject the heat here first to a gas cooler and second to a water cooler, and then the liquid is distributed down into the channel 100 meters below surface, and it comes up again. So this will help to move CERN to more environmental friendly cooling, and the installed capacity will be around 500 kilowatt on one side and 350 on the second side. Now let's have a look on low and medium temperature CO2 systems. I will go shortly into commercial refrigeration, process cooling, and hot water chillers. So CO2 booster systems are currently introduced whenever in Europe a supermarket is replaced. Mainly they go for a CO2 system because it's a very low investment cost and a high energy efficiency, and for supermarkets in Europe and Japan it's a standard right now. Typically you have a low pressure compressor, a high pressure compressor, and rejecting the heat after heat recovery, which is normally placed here. You cool down the gas further in a suction line heat exchanger, and the high pressure control valve flashes the gas into a separation tank. The constant pressure valve keeps the pressure level in this tank and mixes what comes from the low pressure towards the suction line to the high stage compressor. The liquid goes to all the different evaporated chillers, evaporated at the chiller mode, the medium temperature mode, while other liquid goes further down and is throttled into the evaporator of all the freezing cabinets. They help to subcool and superheat. The suction line heat exchanger helps to subcool the liquid but superheats the vapor of the LP compressor, and they again are mixed, and then the loop is closed. Very efficient, very common nowadays. What we have lately developed and proposed for an installation in India is a simpler ejector system where we can support the CO2 with an ejector in an active and passive mode. It depends on the high temperature on the heat rejection device if the ejector is passive or active. When it is active, it sucks all the vapor from the empty evaporators into and pushes them into the separator, and the separator pressure is maintained by the empty compressors. In case we have a low temperature at the outlet of the heat rejection, we have already liquid in the red line, so then we just close the valve into the ejector, we bring the liquid straight to the evaporators, and in that case the empty evaporator passes the vapor through the ejector without any action into the separator, and it is sucked into the empty compressors. Yes, this is very efficient and very simple, and the first systems are built nowadays. More information you can find on this on the proceedings of the Gustav Lorentzen conference, where this concept has also been described more closely. Another interesting system is a DX system for air conditioning for supermarkets. This is a very simple configuration, and the clue is that we go straight with the CO2 straight into the air handling units inside the building. So there is no double indirect loops. What do I mean with double indirect loops? If we have a traditional chiller, the chiller first cools water, the water goes into the air handling units, and it comes back with 12 degrees C, and it's supplied with 7 or something like that. On the other hand of the chiller, mainly we have a evaporative cooling or secondary loop towards a dry cooler, which is the other indirect loop. If we cut out these indirect loops and go straight with CO2 both to the gas cooler, rejecting the heat, and may even use some evaporative cooling at the last part of the gas cooler, we will be very energy efficient and very simple. And our investigation show that this can be more energy efficient than a double loop, which is currently state of the art. We would love to introduce this in an example outside Europe. And last but not least, we're also looking into heat pump chillers for hotels. And traditionally in a hotel, air conditioning and the water heating are separated. Now we want to keep this all together. We see the compressor as the main part of the heat pump in the middle, and it provides hot water, it provides CO2 is cooled to preheat and afterheat the water, which is then supplied to the building with about 70 degrees C. Both building and kitchen can get this temperature. And what comes back from the circulation line is reheated by the CO2, by the water, which has been heated to 75 degrees. Before it rejects some heat to the circulation water, and then it is stored at 70 degrees in these tanks. So the heat pump is charging these tanks, and at the same time the heat pump is producing chilled water for the air conditioning and cooling purpose in the building. And we apply a two-stage evaporation here. One evaporator is on a gravity-fed loop, self-circulation, which is around 45 bar, means 10 degrees C. While the other evaporator is 5 Kelvin lower, 5 bar lower, because the ejector is able to reduce the pressure on the suction side of this evaporator, or the suction of the ejector makes it possible to go 5 Kelvin lower, so we can achieve maybe 10 degrees C at 40 bar. So in this case we can provide very efficient cooling and at the same time utilize the heat to produce the hot water, and that's exactly what you need in a hotel. So a CO2 heat pump chiller for a hotel is a win-win for both the end user and the environment, and it will be a success after all the supermarkets in the next years to come. Now let's have some other interesting clean cooling technologies for example, public transport, cars, and container and trucks, which are utilized in Europe. For example, just to show you, the first car had an air conditioning in 1939, and Gustav Lorentzen, when he invented CO2, he had car air conditioning in his mind. So the very first simple circuit sketch was made like this with the compressor, the gas cooler, an internal heat exchanger, high pressure control valve, the evaporator, and then a low pressure receiver, helping that the evaporator is always flooded, and the suction line heat exchanger makes the compressor safe and superheats the vapor to the compressor. And the innovation was by that time to utilize a high pressure control valve instead of a normal expansion device controlling the superheat. The pressure valve controls the high side pressure actively to achieve the optimum high side pressure to make the best COP of the system depending on the condition. And this is just another way to show it. So what it was used for or initiated for, the energy efficiency of mobile air conditioning. In the early days, nearly 30 years ago, R12 was the common system, and you see on the left hand side here, this is a typical R12 system by that day, and it was built a CO2 system with the same component sizes, and it was found that the COP was even higher with the CO2 system, and this was remarkable by that time, and it gave even a prize at Sinter for this innovation, and the car industry focused on this. A few years later, the car industry picked up the idea and built their systems, and they said soon it's ready. More than 24 years ago, the car industry said it's ready. It took much longer time, even if the performance was outstanding. CO2 had always the slogan, ice cubes in your face. It was so fast in cooling and so on, but it took a while to be introduced. Even in Japan for 20 years ago, they stated that it's 25% more energy efficient than the 134A system. However, it took a while to to get it into the cars. We can skip this one, but we had, even for small cars, it was shown by then that the CO2 system is more energy efficient, meaning it uses less fuel for providing the same amount of cooling, which is also interesting, I guess, for India, because these kind of cars are quite common in India too. Then, about a few years ago, we had the first serial production of cars, of course first in this luxury segment, but anyhow, even in the small electric vehicles now we see that R744 CO2 is utilized as the working fluid, and this is the right way to go. And in Norway, all the ID cars from Volkswagen have CO2 only. So this is a good move. Now I want to show you some examples from a bus, and from both Germany and China, where they utilize CO2. This is a typical CO2 heat pump on a bus, where you have a compressor down in the engine bay of a bus, and the heat exchanger mainly on the roof. And this is typically done for these buses. I show you a picture. These kind of bus, they have this. This is even an electric bus. They have many other buses where they use CO2, and this is the latest version with an electric bus. Even in China, they have understood that CO2 is smart for this kind of purpose, so they have also developed systems for buses and even trains. Even for train, it is utilized, and that's a good thing. And now I want to show you some other examples from transport refrigeration. Refrigerated trucks and containers are also utilizing CO2. This is the latest development of a German manufacturer, Ecoltech. They produce this kind of refrigerated trucks since 1978, and their latest version, this is a previous version, and now this is the latest innovation, and they use on the outside, on this unit, they use propane. So the one I showed you previously, just a clean hydrocarbon on this side, which has a very high energy efficiency, even at high ambient temperatures. On the inside, they use CO2. And this is smart. because then they have never a flammable fluid inside the compartment. The flammable fluid is just on the outside, which is not an issue at all. And they can operate the propane system either in heating or cooling mode. And the CO2 is just inside the body, and it is circulated like a heat pipe principle. So there is no pump or nothing circulating the CO2. It is just by temperature difference and the density difference of the fluid, and it works perfect. Another example is a CO2 container unit, as shown here by Carrier, and they have developed this, and there are several trials and around the globe with this kind of container. And this is a very good application area for natural working fluids, because CO2 is globally available. There is no issue on availability. So this brings me to my summary and the conclusion. Food is valuable and it is very essential for us as a humankind. That's why we need safe and reliable refrigeration equipment to reduce food loss and to make this clean cooling. On the other hand, safety at work is also important for responsible companies. Nobody should become sick due to refrigerants, which cannot be guaranteed with the synthetic fluids. Natural refrigerants, on the other side, are really a safe choice for both end users and the vendors and those who do need to do the service. And we should not forget the environmental impact as a major importance. And only natural working fluids, they will survive towards 2050. So why should you spend money on other fluids in the meantime? And there are great energy efficiency improvements with these fluids. It is just do it. So let's cooperate and focus on clean cooling together. Thank you for your attention. If you have any question, please contact the team in the audience, and also send me an email or visit us on our website for the Indie Plus project. And we are really looking forward to further cooperations. We have also tried to install some demonstration sites in the next years. You will find a description of them here at this website. And I would like to thank you for being with me the last 50 minutes. And if you have any question, please send me an email, and I will come back to you as soon as possible. Thanks again. Have a good afternoon.
Question and answer sessions at the end of third session also. Now we will move on to third lecture. So this is industrial process heating and cooling. This is by Professor Pramod Kumar.
Kumar Reddy, you can take questions. Hello.
Okay. Yes, sir. Yes, sir.
Dr. Shivakumar Reddy, can you hear me?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. I can hear you. We can take, sir.
Hello.
Yes, sir. I can hear you, sir.
Hello, can you hear me?
I can hear you, sir. Yes, sir.
Hello.
I can hear you, sir.
Hello.
I can hear you, sir.
Dr. Reddy,
It's
can
audible,
you
sir.
take questions?
Yes, sir. Okay, sir. Am I audible now, sir? Am I audible, sir? Hello?
Yeah, Dr. Siva, are you audible?
Yes, yes. Okay. So, so many are asking, sir, so will the PPT lectures be sent or made available to the participants? Hello, sir.
Shiva, I think my sir is not getting our audio.
Oh,
Hello,
hello, Maiya sir.
hello.
Yeah,
Ah,
participants wants to ask one question. Sir, please proceed with your question.
Hello.
Yes, sir.
hello. Yes, sir. Audible. Yes, sir.
Sir,
Go
I
on,
am
sir.
Kamal, Dr. Kamal Jyoti speaking.
Oh,
Okay. Yes, sir. Yes,
Sir,
sir.
will
Go on,
this,
sir.
hello?
yeah.
Go on, sir. Go on, sir.
Sir, will this PPT be made available to the participants?
Yeah, I think you see this recording will be a property of the MHRD, I think. Okay. Hello.
Yes, sir.
See,
Yes,
this
sir.
the recording will be a property of the MHRD or SPARC project management or something, and they are probably free to distribute to anybody. I think so. So we will be doing whatever they say. Okay.
Okay. Sir,
Okay.
and one question. Hello.
Yes, please.
So what is this subcritical and transcritical phase?
Subcritical means everything is under subcritical, see, below the critical point.
Okay.
Always supercritical means everything is supercritical. Supercritical gas cycle. That means it is a gas cycle. Everything occurs at this above critical point. Transcritical means some cycle operates between supercritical and subcritical. It just what is see the flights at transatlantic flights. What do you mean by that? What do you mean by that? Transatlantic flights. Europe between Europe and US or North America, right? Flights.
Right.
Transatlantic. That means it crosses the Atlantic Ocean. So though transcritical, that means it these points, this process cross the critical line of points. When you expand, when you compress, it doesn't cross. No, it is always a gaseous state only. When you throttle, the gaseous state will become liquid and again gas. No, two phase. Understood?
Yes, sir.
So transcritical, it crosses the critical line point. That means gas, when you start is a high pressure gas. When you throttle it, become liquid. And then further throttling, it becomes through two phase.
It means transcritical, it is operating between subcritical and supercritical.
Yeah, yes, yes.
Okay, sir.
So like transatlantic flights. Okay, it is transcritical cycle. It crosses the critical point or critical nature because gas becomes liquid and further throttling two phase region. Okay.
So my question is like you mentioned a term person cooling degree days.
Yes.
So actually I was not able to get that what exactly it means, and was it a right parameter to measure the cooling
Yes.
requirements in the
Yes.
Yeah.
It is one good parameter if everybody use air conditioning and cooling. Now only 6% are penetration, only 6% are in India. That means 6% of the people are aware of going for air conditioning or they feel something. Okay, remaining they are not aware of air conditioning at all. But when India is developed, % degree cooling days is a good thing to compare with others. Okay, and ideally, if number in a country, let us take just like weather is just like in India, their population is only 1 crore 30 lakhs. Okay, ours is 100 times more. That means their % degree days is just 1% of our % degree days because temperature is same. Population is our population is persons are more.
Okay, sir. So that is the projected data, not the present one.
Our percent degree days are more, whether our persons are there, degrees are there. Percent, if you estimate percent degree days, it is more. Whether you people use it or not, different is. We need that much of food. People we eat or not, I don't know. We are more, we need more food. People eat or half stomach, we don't know. That is a different story. What is requirement?
So the projected, the presented graph is for the projected value, not the
Yes.
present one.
Present value is just 5% because
Okay.
people are not using it. People are not effort to use. Villagers not there. They are not use it. Our penetration is not there, but it is picking up.
Okay, sir. Thank you, sir.
Any other questions?
Participants can raise your hand if you have any questions.
An ideal system, an efficiency in natural way, how much in percentage? Then please answer what is the efficiency of the Earth planet in our universe. Please explain also. I don't know. I couldn't understand this question from Pramod Kumar Dubey. Pressure limitations of CO2 any? This one question. Pressure limitation is, we are talking about 100 bar, 110 bar, because still higher, we have to need to be our more trained person, better, you know, we can go, because if ambient temperature is going to 45, in my graph you could see the optimum pressure is still higher, up to 120 bar. Okay, so it may be, even if it is 50 degrees centigrade gas cooler exit temperature, you may require to optimum pressure is still higher, but we may not go to that pressure because of high pressure is, again, we need to good expertise in welding, the fluid system fabrication. So as the pressure increases, the safety also becomes a problem. So we limit the pressure to 120, and the valves and pressure regulator may not be available for higher pressures. You know, they come with maximum pressure is 120 bar, 130 bar. So if the available parts are maximum 130 bar, we can't go exceed that. Okay. Then can you utilize the system to reduce the CO2 emission in our environment? So we see how to produce carbon dioxide. We don't take the carbon dioxide from ambient air. It is hardly 420 ppm, parts per million. Okay, if you take 1 million unit of ambient air, you will get only 400 parts. So it is like maybe getting gold from ocean water. It has also got gold, no? Ocean water has also got gold. You know, we can't take gold from there because the extraction cost will be exorbitant. So similarly, CO2 cannot be extracted like that. Better to be, maybe you can, you know, you have to absorb carbon dioxide and push it to the earth to reduce the sequestration from the plant. Okay, not from ambient air, only from the plant. So normally we produce carbon dioxide from the refineries where we are burning something, and carbon dioxide is produced in high concentration. Okay, that is what we produce carbon dioxide, not from ambient air. This system, carbon dioxide reference system, is a refrigerant. It may also leak. It will go to the ambient. And we don't trap it back from ambient air to this. Not possible. We manufacture or get carbon dioxide from the refineries or power generating unit where carbon dioxide concentration is very high. Please share feedback link of today. Feedback, I don't know what is it. Do we get recording of the meeting? I already told we are subject to SPAR, the MHRD ministry, and our dean, whatever they say, we will do. It's recorded and we'll hand over to them. Can you please share your email ID? Whose is L. Saravana Kumar? It is already there in our slides or recording. I don't know. Mine is. I'll write in my chat box. If you could available official NPT, great. If it could be available on official NPTEL YouTube channel, again I don't know. We'll do whatever our boss says. Wonderful session, Professor. Thank you. Thank you. Happy to. Thank you. Thank you. Real. Sir, kindly share the PPT. We'll see. Definitely. Thank you for the wonderful session. Okay. We can wait, no problem. Vishak,
Yes,
Professor Pradeep Pramod Kumar told that he will complete in half an hour or so. I will just complete these questions. When refrigerant enters in supercritical, then it will behave like a perfect gas. If yes, then transcritical has advantage of perfect gas behavior also. No, there are two parts of it. It will behave like a perfect gas. No, it is highly a real gas. Okay, this specific heat changes. You can see the line. It is not straight line. It is like a snake. At the critical point, all the properties will abruptly change. CP values will change very significantly. It's no more a perfect gas. If yes, it is no. Okay, then the critical transcritical has advantage of perfect gas behavior also. No, it is a even if a real gas, there is no advantage. Even if perfect gas also, there is no advantage because it's a gaseous cycle. At the end of the gas cooler, it's a high pressure gas, lot of energy. When you throttle, all the energy is destroyed. So we need to go for ejector or expander to recover the work energy from there. Sir, what is aspiration? It is a carbon dioxide concentration. You will not be able to. So see, the blood requires oxygen. No, when you inhale, oxygen will go to the blood, and in the lungs, this exchange takes place. Oxygen goes into the blood, carbon dioxide goes out from the blood. So that's how you get the oxygen into the blood. The food gets burned, CO2 is generated, and that will come to the blood and back to lungs, and even exhale it comes out. So when carbon dioxide concentration is say 10,000 ppm, your blood cannot give out carbon dioxide to the in the lungs. It can't exchange. So carbon dioxide concentration blood will increase. So when the CO2 concentration exceeds 10,000 ppm or 15,000 ppm, that is a situation where expiration takes place. Any attendance link or feedback link today? Any attendance link or feedback link today? Dr. Reddy? I am seeing the questions.
Yes, sir. Attendance will be recorded by the Zoom itself. Feedback we will share it. Feedback link we will share.
Okay. Most of the emissions of automobile is CO2. Can we use that emission to cool the engine and raise the efficiency? No. See, emission is CO2 and it goes to atmosphere. We are using CO2 as a working fluid within the cycle. So compress CO2 gas, cool it, throttle it, then it will come at low temperature and it absorbs heat. It's in a closed cycle. Whatever carbon dioxide produced by engine and by engine by burning fuel, it goes to ambient, by polluting the ambient. Okay, this question, we can't use the CO2 that is going out, the exhaust gas, for cooling anything. Not possible. Is it possible, suitable for low capacity system? Yes, it will be possible when this smaller compressor available and the system become very compact, still very small, tiny compressor, because it's have at high pressure, density is more. Professor Armin also elaborated on that. What could be cost of per tier for low temperature cold storage system compared to conventional one? This really I don't know. Right now the cost may be little higher, much higher, because compressor and most of the components has to be imported. When there's a turnover that more and more people use the carbon dioxide system, then definitely there's a price parity will be there. How we can find suitable refrigerant for cascade system, and can we use more than 2 refrigerant in a single cascade system? Why to use more than 2 refrigerants? So no need. Cascade means 2 cascade. Bottoming cycle is CO2, topping cycle either can be hydrocarbon or ammonia. If you're going for natural refrigerant, people use some other synthetic refrigerant also, but we recommend bottoming cycle, low temperature bottoming cycle, CO2, topping cycle, ammonia or hydrocarbon. So that the bottoming cycle also, CO2 also works under subcritical, where the gas after the compressor condenses. No need of going for more than 2 refrigerants. I don't know if somebody has got a specific requirements of 3 refrigerants, we have to see how we can use 3. Topping cycle can have 2 refrigerants also, or you can have cascade, bottoming cycle, middle cycle and top cycle. If the temperature lift is too high, let us take, you want to go for really -70 degrees centigrade bottom, and you are in Dubai where temperature is 60-70 degrees centigrade ambient temperature, maybe cascade 3 may be okay. Is it possible to utilize carbon dioxide emitted from persons in refrigeration system? No, it's not possible. Is it possible to utilize carbon dioxide emitted from persons in refrigeration of room or vehicle? No, because we're exhaling, it goes to ambient, and when the exhaling here, the ppm may be, I don't know, it may be about 3000 ppm or 4000, 3000 or 4000 ppm, very small. We have to use CO2 in a closed system with a compressor, gas cooler or condenser, throttling device, and this. Whatever carbon dioxide is available in the general air, it cannot be used for cooling. So what we exhale, it goes to ambient. The decomposition of HFOs and product of TFAs proven. We can find literature in favor as well as against this reaction. There is no favor, only against. This is proven, as Professor Armin also elaborated. There's so much research. The TFAs are formed, which goes into water, and it will be there. It can't come out. It will be. You got stuck with that. So as we keep on using HFOs, more and more TFOs will be formed. TFAs will be formed, and will go to the water. So after some time, then people say, no, we can't use HFOs. You have to be face down. You face out, because it will pollute the water. That such situation will come another 10, 15, 20 years. Pramod Kumar, thank you, sir. Okay, thank you. If I join little late, how to post my attendance? I know, sir. If I join little late, how to post my attendance? That Dr. Shivakumar will answer. CO2 is toxic. If you use this system in residence without much airflow, is there any security threat? See, CO2, it has to in the toxic if you use in the system, the residence. Okay, at present it is not used for the residences, commercial air conditioning only at present. depending upon the small system, how much CO2 will be there. So you have to be, we should cross about 15,000 ppm, and a small system, if it releases, it won't cross that much, according to me. So it should not be a problem. But presently we use it in a commercial system only. Okay, zoom. So Shivkumar already answered that question. Okay. Thank you. So Sunil Kumar, to everyone. Sir, is it possible to store CO2 emitted from automobile and use it for refrigeration? No, not possible. We can't store it. No, it goes out. How to store the, that too is not 100% CO2. No, it has got a lot of water, the air, unburnt gases, other emissions, some CO2. Maybe, I don't know, maybe 20% CO2, depending upon the fuel, 20% CO2. That is not possible. If you want to, if you can collect, and you have to purify CO2. So we are using in the system 99.99% CO2 or 99.999 food grade CO2 we are here to charge. Whatever carbon dioxide is for Coca-Cola or soft drink companies, we use that 99.999% pure. Okay, this, if it is maybe easy to use this automobile exhaust into Coca-Cola, probably that it will absorb carbon dioxide and you can will be able to drink that Coca-Cola. So the carbon dioxide that will be used in the system should be pure, otherwise your components will go. Okay, we can't just use that as it is. So how much CO2 superior to ethane or ethane refrigerant? See, yeah, see, you have to compare. Ethane is as it is not used, refrigerant as it is ethane and ethane group of refrigerants. You know, R22 is a ethane group. Knock down hydrogen, add chlorine, add fluorine, things like that. So that is a ethane group refrigerants were used, and some of things are used still. Okay. Thank you. I think Dr. Shivkumar.
Yes, sir.
So you can take over and introduce our Professor Pramod Kumar, and then Pramod Kumar will take over. Thank you.
Thank you, sir. So now we'll move on to the third lecture, so which is industrial process heating and cooling with CO2 as refrigerant. So by Professor Pramod Kumar. So Pramod Kumar is an associate professor at Department of Mechanical Engineering at IISc Bangalore. He obtained his master's and PhD degrees in mechanical engineering from IISc. Prior to joining IISc as faculty, he worked as a research engineer at Georgia Institute of Technology, Atlanta. Dr. Pramod Kumar has numerous awards to his credit. He is a gold medalist at IISc for his doctoral research, recipient of KSCST Professor Satish Dhawan Engineer Award for 2018, Dr. Abdul Kalam Award for Outstanding Engineering Contribution for year 2021. In the 2020, he was elected as Fellow of Indian National Academy of Engineering. Dr. Pramod Kumar works broadly in the area of design on thermal systems. Currently, his team designed and developed a 100 kilowatt transcritical CO2 refrigeration system for ship cooling for Indian Navy. Additionally, his team is involved in developing India's first supercritical CO2 power generation system. So, this is a short biodata of Pramod Kumar, sir. Now, I would like to invite Pramod Kumar, sir, to deliver his lecture. Pramod, sir.
Yes, good evening to all of you, and thanks, Dr. Shivkumar, for the introduction. So, I will share my screen and I'll keep it short for today. Here. Are you able to see the screen?
Yes, sir.
So, we have about half an hour. So I'll try to finish my presentation in 20 minutes because most of these slides that are there in this presentation have been already covered in the previous 2 sessions. Okay, so let me get into the presentation mode. We're going to look at industrial heating, process heating and cooling with CO2 as a working fluid. This is the topic of my presentation. But largely, the slides are not going to be any different than what Professor Maiya or Professor Hafner has presented. Okay. I'll only add a few things to what Professor Maiya presented. So just in academic interest, so how does the number 744 is designated to carbon dioxide? So if you look at the refrigerant nomenclature, this is an international agreement. So R stands for refrigerant. Then it is followed by 2 or 3 numbers and then 1 or 2 letters. Okay, so briefly going into propane, which is a natural refrigerant. So 2 stands for propane series. So R290 is actually essentially propane. Then if you look at 6, then it is organic composition. So butane will be R600 and isobutane is R600A. And then inorganic compounds are ammonia, water, and carbon dioxide. So all of them start with 7. Then this is the molecular weight of water, and this is the molecular weight of carbon dioxide. Okay. So again, this is again a repeat slide, so bear with me. So essentially, as Professor Armin mentioned, see, ODP and GWP are relative definitions that probably need to be revisited again. But then, I think in the future generations to come, people would forget what is ODP because we'll soon phase out almost all refrigerants that are ozone depleting in nature have been phased out. They primarily contain chlorine or bromine. Okay, the current systems that are already having chlorine and bromine are going to be, retired by 2030. The world will not see any more systems that will contain any of the refrigerants that contain chlorine or bromine. So in terms of global warming potential, GWP of CO2 is the benchmark, so it is 1. So every other refrigerant would have a basis based on the CO2, the global warming potential of CO2. For example, CFC has got a GWP of about 5,000, whereas water has got probably, this is the only refrigerant that has a GWP of 0. Okay. So again, I will not get into more details on this. So essentially what it means is that the F-gas regulation, the European Union has already moved largely into the usage of natural refrigerants. So India also is a signatory to the Kigali Agreement and says that it is, and also the Paris Agreement, saying that we will actually cut down the greenhouse emission, the refrigerant that causes greenhouse emissions by 2047, and then by 2047 we should be completely done away with any synthetic refrigerants will move completely towards natural refrigerants. So in terms of medium and long-term refrigerants, let me just. So we are looking at, of course, the chlorofluorocarbons or hydrofluorocarbons have been completely now banned. Okay, so the world no longer produces any CFC refrigerants. Now you have low GWP, which are either HFO or R32 that are currently being used. 1, 2, 3, 4, YF and ZE are being used. And then you now have natural refrigerants which are completely halogen free. So R717 is, sorry, this should have been 718, I guess. So is water. R290 is propane. And then R744 is carbon dioxide. And then you can also have blends of any of these natural refrigerants. Okay, so the GWP, if you look at it, only water has got lower than that of carbon dioxide, and rest all of them would have a GWP higher than carbon dioxide. Okay, so again, depending on the hydrocarbon content, these refrigerants become flammable. So propane and butane are highly flammable refrigerants. They are classified as A3, category A3. And then R717 is now B2L, that means it's completely non-flammable. Okay, and 744 is also it's non-flammable. This is non-flammable and non-toxic as well. So in terms of again, this is again a repeat. So what we really want to be in this lower end corner of it, which completely is natural. These are all. This is the quadrant that uses all natural refrigerants out here with very low GWP and nearly almost zero ODP. Okay, or completely zero ODP. So this is where we would like to be there, and primarily would like to move towards ammonia, carbon dioxide, and propane. So again, the intent is that we want to reduce the global temperatures. So the mean sea levels would rise, but Professor Maiya mentioned that till 20 centimeters of sea level rise will cause most of the coastal cities to flood. So it is important that we reduce our greenhouse emissions and bring down and arrest this increasing global temperature increase. Okay. So this is what and why this particular topic of moving towards natural refrigerants is so very important, that by moving towards natural refrigerants, not only you reduce the potential for harmful greenhouse gases emissions, but also the production of natural refrigerants occur naturally. So you don't really have to produce natural refrigerants. Like for carbon dioxide occurs naturally. So essentially, by reducing the production of synthetic refrigerants, you're contributing significantly to the global warming potential, which Professor Hafner mentioned that the definition of ODP and GWP also need to account the amount of emissions that are emitted during the production of these refrigerants. Okay. So again, by 2047, we will have complete phase down of HFC. So the whole world will move towards a complete usage of all natural refrigerants by 2047. Okay. So historically, if you look at it, carbon dioxide is before this chemical evolution, in between the early 20th century, where there was a lot of emphasis on creating new chemicals and synthesis that took place. Before that, there were only probably two very good refrigerants, ammonia and carbon dioxide, that were widely used as a refrigerant. There were a lot of attempts made to actually build compressors for carbon dioxide and ammonia. So carbon dioxide being, high pressure refrigerant, so there were a lot of leakages. So the system did have its own set of issues in the early stages of the industrial world. But then slowly, with the advent of synthetic refrigerants, this completely carbon dioxide was just written down in history. But then way back in early 1990s, Professor Gustav Lorentzen, actually, where there's also a conference named after him, he was the pioneering champion who brought back natural refrigerants to arrest this global warming issues that came out, and the ODP issues that came up into the light in the late 1980s and early 1990s. So if you look at a timeline, the subcritical cascades were really credited, I would say, to Professor Gustav Lorentzen's team that really worked on bringing back carbon dioxide from what it has been really discounted in the early 60s. And then a lot of the European Union, basically the European countries, started implementing and using natural refrigerants because of their benefits and non-harmful nature to the environment. But then as the popularity of using natural refrigerants grew, then so was the technologies, and in terms of the system components that are available for carbon dioxide and other high pressure refrigerants, and also the manufacturing technologies evolved. And now we have a host of industrial products that are market ready to be deployed, like vapor ejectors, liquid ejectors, and multi-ejectors that are readily available off the shelf, which you can just pick and drop and build a natural refrigeration system. So now, if you really look at it, the market is really ripe and ready, where everything has been ironed out. A lot of issues have been ironed out in terms of arresting leakages and system performance. You can now get very robust systems can be built with carbon dioxide as a refrigerant. So of course, I'm not going to get into this. What it just tells you is that you can, with carbon dioxide above 1 atmosphere, that means above the atmospheric pressure, you can still achieve close to about -50 to -55 degrees Celsius, because the triple point is close to about minus 57 degrees Celsius, and still it is substantially higher than the atmospheric pressure of 1 bar. Okay, and then the flip side of it is that since the critical temperature is low, where most of the ambient environments around the world are there, so you need to operate the system in a transcritical mode. We'll get back to that. We'll get back to this topic a little later. So, of course, one of the main advantages of carbon dioxide, if you look at in the supercritical phase, once you heat it and this entire system, actually when the pressure goes to about 74 bar, you can see completely a crystal clear side glass that shows that the carbon dioxide actually has the density of that of a liquid, and then yet behaves like a gas in terms of occupying the entire volume. So this has got tremendous advantages both in terms of power generation and refrigeration. So okay. So there were some questions on the properties, and yes, so in terms of properties, carbon dioxide is actually does not exhibit a real ideal gas behavior. It is a perfect, I would say, a real gas. You see a lot of non-linearities in the temperature in the variation of all the transport properties closer to the critical point. So that means that the system has to be very carefully designed, taking into consideration the real gas properties and behavior of carbon dioxide. So a lot of these issues are associated when you come closer to the to essentially the critical point. You find that these artifacts of operating in the pseudo-critical region creeping there, and then suddenly you'll see a significant rise in the compression power that is only attributed to a large increase in the specific heat and density closer to the critical point. And again, what it means also in terms of heat transfer, when you're looking at developing gas coolers, particularly gas coolers which are operating in the transcritical region, or it is also undergoing subcritical gas coolers, you have to ensure that you adequately have captured the property variations of carbon dioxide in the region of operation, where you find that there is a large density variation. See, these are all the ideal gas behavior, and then this is superposed with carbon dioxide properties. So you see that how much of a deviation is there from the ideal gas behavior. So in this region here, while most of our operations in transcritical refrigeration take place, you have to ensure that these points of inflections are adequately accounted for in your heat exchanger design. Again, what it means is, in terms for a thermodynamist, this is CO2 is an excellent working fluid. It gives you a host of cycles that one can really imagine. You can get completely superheated rear cycles. You can have transcritical cycles, or you can also have supercritical cycles, or you can have a combination of many of these cycles to produce either power generation or refrigeration. So this probably is the only fluid that is practically feasible to combine both power and refrigeration cycle. So it gives you an opportunity to produce cooling as well as generating power within a single circuit without having to change or have an intermediate fluid. So there were a lot of questions on how does it actually differ from a standard refrigeration cycle? How does a transcritical CO2 cycle differ from the standard refrigeration cycle? So in a nutshell, in single answer, what it means that everything, all conventional refrigeration cycles, including propane or isobutane or even R32, actually operate within the dome. So your entire cycle operates within the dome here. And that means that when you're operating in the two-phase region, you're locked in by both temperature and pressure. So you don't have the flexibility to change the pressure independent of the temperature. So depending on your ambient condition, this line 3 to 4, this pressure is going to be decided. Whereas in a transcritical cycle, you now have independent freedom to push this as high as you want. And then you can now control the quantum of cooling by just, we'll come shortly to it. But if you keep pushing higher and higher, then it does certainly have an effect on the quantum of cooling that you can get. And also in terms of heat pump, you can now go to much higher and higher temperature, yet being in the, because now you're outside this dome here, outside the critical point. So in terms of the heat transport properties, as Professor Maiya also mentioned, see, whereas in a conventional subcritical cycle, you now are hit by this flat lines which are there inside the two-phase region. But in a supercritical regime, when heat transfer takes place and above the critical point, then now you have, this is the kind of heat transfer characteristic. So you have to be very careful when you select another working fluid that undergoes phase change and is exchanging heat with carbon dioxide. So these are some of the things that you need to look at into your engineering aspect when you build or develop a heat exchanger or for a transcritical system. So I'm sure that in the next tomorrow or day after tomorrow, Mr. Kamath from Danfoss also will talk a little bit more on the controls. But this just tells you that, as you keep increasing the pressure, you see that the COP actually of the system goes up to a certain pressure, and then this is the knee of the isotherm. But if you go beyond this, then you realize that you get a diminishing return. The amount of cooling effect that you get to the amount of power that goes into the compression actually becomes significantly large. So fortunately, all of these have been programmed in most standard controllers that are available for carbon dioxide. So you don't have to really split hair in terms of how do you select the optimum pressure. Okay. So this is what is again, as the slide says, it's from Danfoss. This is how the Danfoss controller operates, and it continuously will keep on monitoring the ambient condition and adjust the compressor discharge pressure. It will command the compressor to continuously adjust its discharge pressure to ensure that you are at an optimum operating point. Okay, in terms of the number of cycle configurations, I'll go very quickly on this. So Professor Maiya and Professor Hafner have explained in great detail that you can now have enormous flexibility in selecting components and designing your carbon dioxide transcritical CO2 systems depending on specific tailored needs of evaporating and gas cooler temperature and the applications that you would need. So in a nutshell, what it means is, in the recent years, there have been a significant amount of improvements in the transcritical CO2 refrigeration space, and this is continuing to grow tremendously. A lot of new systems, as Professor Maiya also mentioned, that recovery of the the energy from the throttling device. A lot of new work as an expander is also being actually done in a couple of places that I know in US. There is a lot of work that has been done to ensure that you can recover this energy and feed it back to the compressor to reduce its work of compression. So we will certainly see more and new systems that will come in and make the CO2 systems a lot more efficient in the days to come. So these are the current amount of technologies that are available with transcritical CO2 systems. You have multi-stage compression, you have parallel compression, internal heat exchanger, then this expander is being certainly looked into. You can go for cascade systems, you can look at ejector, and you can look at a multi-utility system with different slabs of evaporation temperatures to produce different kind of cooling and heating requirements. So this again, I think Professor Maiya has mentioned in great detail, so I'll not go deeper into it. Okay, so let me come to, this was what I was talking about in terms of when you're looking at heat transfer in the supercritical phase, you have to ensure that, of course, the water is going to undergo single phase heat transfer because you're below 100 degrees Celsius. But then when you do that, you have to ensure that, this large delta T, okay, that you have to minimize so that you can reduce the exergetic losses and have this as close to hugging this as close to this isotherm to ensure that you have efficient heat transfer that takes place. So sizing of the heat exchanger and selection is very important. Okay, another thing, of course, Dr. Pradeep Gupta will also talk shortly on the ejector, but then he'll give a detailed presentation on probably how an ejector works. But what ejector means is this is one of the devices to ensure that you can recover partially the energy from the high pressure stream discharging the exit of the gas cooler to lift the subcritical carbon dioxide discharge from the evaporator to an intermediate pressure to reduce this compressor work. This technology is now fairly matured. A lot of components and also the cycle is is available with most commercial manufacturers like Danfoss, Carroll, etc. So all of this is pre-programmed. Now, this shows just a system with how an ejector is used. Well, now looking at what are the typical applications for carbon dioxide. So a lot of the space has been now refrigeration space, at every application that was traditionally used by synthetic refrigerants, now carbon dioxide has certainly entered into it, including the automotive space also. It has entered into it. Okay, so now these are some of the installations that are available worldwide. You can certainly look at r744.com, and then you can get a lot more insights into the traditional carbon dioxide systems that have been deployed worldwide. So this application, which we will not see in India, so it is worthwhile certainly mentioning, is about ice. One second. Ice rinks, actually. So where you look at this entire thing is frozen. So the entire field is frozen with ice. So this is a very nice application in the sense where CO2 perfectly fits the bill, is that you need low temperature cooling to maintain this ice. Okay, because as you keep moving, the friction between the ice keys and the ice sheet is going to cause the ice sheet to melt off. So you really need to keep it cold so that it remains as ice. But at the same time, the audience who are sitting around this ice ring also actually need to be heated. You cannot be staying at -10 or -12 degrees Celsius out here and then watch the game. So basically, you need both simultaneous heating and cooling, and this is a perfect example for application candidate for a transcritical CO2 system. So what this typically the system does is that now you have coolers that actually produce and maintain the ice. And at the same time, the heat that is rejected is now used for heating the auditorium where the audience actually sit. So these are the ice rink is a classic example where the entire both the cooling and the heating effect of carbon dioxide is efficiently utilized. Okay, this will not get into it. So in terms of what for Indian perspective is, CO2 has the potential now to actually replace your entire supermarket with just one system. So you can have one system with multiple level of ejectors, with different level of cascade compressors mounted on a rack with very compact spaces, and you can now have evaporating, air conditioning, deep freezing, as well as heating, all in a single system. So it's just possible in one system. So this is really the advantage, and this is where the whole world is going towards. So these are some of the examples that CO2 systems typically allow you to have very clean rooms where basically the workrooms or the floor spaces where you can now have rack mounted systems with multiple compressors, and all of them can produce very large tonnage, close to about of the order of 3 to 5 megawatt of cooling can be produced with a very compact CO2 systems, and that is where the beauty of the system actually lies. So in terms of the systems that are deployed in India, yes, IIT Madras was probably the first system that actually had a working transcritical CO2 system that was built exclusively for refrigeration applications. So if you are around IIT Madras, or if you happen to go there, certainly have a look at that system. Now, these numbers, this is 2020, but I think it is certainly increasing. A lot more of this numbers have gone up in the last 2 years. So you find a significant rise in US also. There is a greater adaptability of transcritical CO2 systems worldwide. So this is a nice survey which talks about what is the market share of CO2 systems. You find that supermarkets and industrial sites are actually the biggest contributors of the applications of carbon dioxide. Of course, in countries, mostly Asian countries, you find that small stores also are utilizing transcritical CO2 systems. But in Europe and US, it's essentially the supermarkets, large supermarkets, that actually comprise of the share of the CO2 system. So this again is what are the revenue and assets that are projected with carbon dioxide based systems. So you find that this trend is continually increasing, and it is going to explode in an exponential manner from 2030 onwards, when the real phase out of the synthetic refrigerants take place. So there is a nice article, and I will not get into it, but you can go to the World Guide to Transcritical CO2 Refrigeration, 2020. This is available freely on r744.com, and it's a very good document. And this has been compiled using the data that is available in this. So there were a lot of surveys, people who are asked that would they like to move to a transcritical CO2 system. And if you look at these numbers, everybody says that yes, they are willing to look into a transcritical CO2 system, provided there is a robust market supplier. There is a supplier that can actually develop robust systems. So that means that there is a huge potential for investment and moving towards natural refrigerants, because the global warming is something that you and I cannot escape. So the whole world gets affected by it. So I think, as Professor Hafner mentioned, that it is a responsibility of all of us to ensure that we move towards these refrigerants to make the world an environmentally safe place. So I'm not going to get into this part of it in detail, but there are some interesting things. But if you look at these numbers, many people say that CO2 is not very efficient, but actually that fact is not very true. We have built our own CO2 systems, and there are places where CO2 will certainly ace out HFCs or an HFO system. So it depends on how you view it. Okay, so this certainly we can talk a little bit more on it, but certainly what is needed is that, and they are not very difficult to maintain as well. It's only you have to be a little bit, you have to build them robustly, but if you actually build them robustly, they will work for a lifetime. We have had no issues in the last 7 years of which we have actually built CO2 systems. They have been absolutely safe. We have never had any issue of leakage, but you have to build it right in the beginning. So this is what Professor Hafner had mentioned about a supermarket site, which talks about, for India specifically, with combined heating, cooling, deep freezing, and air conditioning. And again, this is one slide I'd like to spend a little bit more time on this, that in India, there is a huge potential for elevating the temperature of waste heat, So one of it is, this is one of the emerging applications where high temperature heat pumps are being looked into carbon dioxide. The potential problem is now that we don't have a suitable oil that goes beyond 165 degrees Celsius. And also the insulation in the compressors permit you to only go up to about 150 degrees C as the discharge temperature. But once we move towards higher than class H insulation in the motors, or basically we move away from the suction gas cooled compressors, then we'll be able to go to much higher temperatures with carbon dioxide based heat pumps. Okay, so this is another research work that we had looked at, where we had looked at utilizing the heat from the primary vapor compression refrigeration system to run a secondary VRS system. This also can be used to run, a vapor adsorption system also. So we can do many different novel things with transcritical CO2 cycles. So I'll not come to it. This I'm going to go quickly over this. So this again, Professor Hafner has mentioned about it. Okay. So what we'd like to tell you is that if you look at this COP of propane, propane is quite similar to 134A. And if you look at a CO2 direct heat exchanger unit, the difference is not much. You're very close to, in fact, you're sometimes better off with carbon dioxide based direct heat exchanger unit compared to a propane based chiller. So if you look at it in terms of COPs, our own experience has been that if you design the system correctly and if you size the heat exchangers properly, then you should be able to get very close to the system COPs of what 134A or any of the existing systems are. Okay. So another important thing is that now you can combine transcritical and subcritical systems to produce cascade systems. This I'm not going to go into the details of it. One gaining popularity worldwide is essentially going for a two-stage system with carbon dioxide as the circulating medium instead of actually using brine. And then the high stage system is with ammonia. So this is gaining popularity worldwide. Okay, so this again we have gone to. So what it tells you is that, see, if you're actually with carbon dioxide system, you can still go to close to about minus 55 degrees Celsius and still operate in above the atmospheric pressure. So that offers a great deal of simplicity in the system, that you will not be operating under vacuum where there's potentially air can get into the system. Okay, so this is I would like to spend about 5 minutes on this particular and 2-3 slides now. So what it means is, where we have real challenges with the carbon dioxide systems is that although your pressure ratios are pretty small, with carbon dioxide, the pressure ratio is 3.1 as compared to about 5 with 134A, but your threshold pressures are significantly high. So that means that you are now operating close to about, say, from 40 bar to about 110, 120 bar, so essentially it means that your system is much more prone to leakages. Okay, so the advantage that you have in terms of operating at much significantly higher pressures, like for example, 1 Kelvin is 1 bar, the pipe losses are very low. You don't have to worry about pressure drops in the system. Heat exchangers can be very tightly spaced or the plates in a plate heat exchanger can be very tightly spaced. You still, without having a penalty on pressure drop, you can get significantly better performance. The flip side is that your system has to be built very well. If you have small issues, then it can pretty much leak. The carbon dioxide will leak at an alarming rate. Then you'll find that within a couple of minutes that you have actually the system has actually vented out carbon dioxide. So that is one of the biggest disadvantage that you have with the carbon dioxide. But then again, that only means that you need to now elevate your workmanship in terms of when you build the systems. Another advantage, and this is where we have seen firsthand experiences, CO2 actually gets very close to your theoretical predicted COPs. So you don't have to have a scaling factor like in 134A that, okay, it will perform 80% of my theoretical predicted efficiency. Here it will perform close to about 90-95% of what the theoretical efficiency shows. So now you can build more reliable and predictive systems, and you can have very robust control systems compared to what you would get with synthetic refrigerants. So again, this is a slide that I would let Mr. Kamath explain day after tomorrow or so, in terms of the discharge line sizes. When you look at 134A is the most popular flow refrigerant worldwide. So all this comparison with respect to 134A, if you look at, see, for a similar capacity 134A system, your line size is less than half. So that means that although you operate at higher pressures with thicker tube wall thicknesses, but your line sizes are significantly smaller. So it means that it significantly shrinks down the system size. Okay. So now this is again a slide that probably it'll be better if Mr. Kamath explains, but what it means is that now with transcritical CO2 systems, this is the world of IoT. So everything is going towards fully electronic controls. You don't have to go and adjust or do any mechanical adjustments. All of it will be done by a computer in real time, where even the phase diagram of carbon dioxide is completely built into the controller. So of course, the controllers are a little expensive right now, but once numbers increase, we find that this is going to be more sustainable, and carbon dioxide systems are going to become cheaper as we move on. Okay. So this is one place that we would like to look into, and this is what we also have been studying. So carbon dioxide is notorious in its supercritical state that it is a very good solvent. So it is used for coffee extraction. It is also used for waterless washing machines and stuff like that. But the flip side of it is that it ends up actually damaging these rings. So O-rings actually get damaged. Okay, so this is a problematic concern, especially with transcritical CO2 systems. So we have had first-hand experience where we find that all of a sudden there are O-ring failures in multiple places. So when you look at it, there is a phenomena called explosive decomposition, where carbon dioxide at high pressure will go and dissolve the polymer inside this, the elastomer inside this O-ring. And once it's depressurized, it will just come out at supersonic speeds, causing small blisters on the O-ring. So this is one of the issues that are typically faced. So new materials are being invented that can actually withstand this kind of explosive decomposition. So in terms of safety aspects, there was a question on axial-fixation. So axial-fixation means that you're essentially displacing air, oxygen, from the atmosphere. So if you're in a room, then carbon dioxide, being much heavier with a molecular weight of 44, will tend to displace air. So carbon dioxide also being inert, it's not poisonous. Okay, so there were questions saying that is carbon dioxide poisonous? Carbon dioxide is absolutely not poisonous. It is only that when you feel that there is loss of breathlessness because it has displaced air. Okay, so it causes death because of asphyxiation, not because that it is poisonous. Okay, so if you find signs of discomfort, that means that there is actually loss of oxygen supply. So this is something that you need to be really careful when you build CO2 systems. So you need to have at least a CO2 leak detector that is installed and will give you an alarm if there is leakage of carbon dioxide. Or you should take potential leakage paths and push it out of the room so that it can be installed in an open environment. Okay, so this is a test loop that we have built in 2015 or 16. This does both, is primarily meant for power generation, but it also works on refrigeration mode. And in the last 5 or 6 years, we never had a single leakage issue in the system, and it has worked very robustly. But as I said, that you have to build it right in the beginning on the when you build the system. This is another one that recently was developed for a naval application. This was developed along with Triveni turbines in collaboration with Triveni turbines. So this Bay Area is essentially where it was actually manufactured at Triveni turbines, and it has gone to for land-based testing on a naval base. So this produces about 100 kilowatts of cooling. In fact, the system it performed so well that we are now able to get about nearly close to about 130 kilowatts of cooling for a system design that was originally meant for about 100 kilowatts of cooling. So this is what I said, that it is very surprising that the system actually will outperform your expectations. So this is the real truth of carbon dioxide based systems. So this is how the system works. So it's a very simple system that you have a gas bypass system with 2 compressors, one standby compressor, and you can get very close to, and it'll always maintain an optimum compressor speed to ensure that now you have optimum cooling that is available across the evaporator. The main advantage of the system is that the cooling is almost instantaneous, so unlike R134A or something where the system has its own inertia, with carbon dioxide system, that inertia is extremely small. The moment you turn on the system, you will find that it starts producing cooling. Okay, so specific issues with India is one is, of course, the with carbon dioxide based systems, the pressures are significantly higher. So you're operating at close to 100, 120 bar, and every rise in pressure above, say, 20 bar is actually quite risky. So you have to ensure that your systems are very well designed, you have to ensure that your pipe standards, welding standards are actually maintained. I would recommend that you should go for all stainless steel or copper construction with orbital weld systems. Then there is always a question, which one is better, welding or brazing? It depends on who performs it actually. So if you go with brazing, it is certainly silver brazing. Then there is also, so this is what is really puzzling, is even in the compressor, there are oil level separators or oil separators and oil level switches which are supplied by third party. It's what is surprising is that why are the compressor manufacturers not providing these as a standard optional or standard systems on their compressors? The oil management is again a third party device. So when you build new systems, you have to learn a lot in terms of how to integrate so many system devices from so many different vendors and ensure that the handshaking is correct. So that has been our biggest problem in terms of building systems. Another issue is that the valves are having different alloys and different metals, and when you weld stainless steel to these metals or alloys, then you find that there are cracks. So you need to find appropriate welding filler material. You have to go back to the manufacturer and ask what is the MOC. So there are a lot of concerns in terms of when you actually start building the system, you will find that suddenly there are weld cracks, how it has to be cooled. So these are things that are not openly available. The only way to learn it is that you have to start building the system. Okay. So I think another important thing that I would say is that we have a very good corrosion lab on CO2 based corrosion, and we have seen that the biggest culprit is the water level, the moisture level inside carbon dioxide. So obviously, thermodynamically, you can never get a perfectly pure gas at all. If it is contaminated to some extent. Depends on how many .9999 you can have, but it's never going to be 100%. So what is the percentage of contaminant is going to be a major issue. Main thing that we have seen is that you should not have any sulfur or moisture. So it does have penalty on the performance due to contamination of carbon dioxide. But how much is it? We don't have an answer. It can certainly, the big flip side of it is that contamination in carbon dioxide can offset your completely your inbuilt parameters on your controllers, because they all assume that your carbon dioxide you're filling in is pure. So there are issues of that sort. These oils are again, they can be harmful to the environment. So the discharge of these oils, polyester oil and PAG oils, have to be done correctly. And you should avoid intermixing during system maintenance. You have to drain it out and refill it. So these are some of the issues that are certainly can be addressed, but these are addressable issues that are hindrance to the development of this SCO2 systems, particularly when you're building it for the first time. Yeah, I think that is it. So I would like to acknowledge, we have learned a lot of things from Professor Maiya and Professor Hafner. And of course, Dr. Simarpreet is also there, and my ex-student, Dr. Kundan Kumar and Pradeep Gupta. So they have been very helpful in preparing this presentation slides, and also Vinod Lagori, who is my current student here. So I would also like to acknowledge Danfoss India Limited and Triveni Turbines for an extensive financial support that has actually helped us in developing these systems that are there in the lab. Okay, thank you. So if there are any questions, we can. It's already a little late, maybe 10 minutes past 7, but if there are any questions, we can certainly look into.
So participants, if you have any questions, you can raise your hand or you can post in the chat box.
There is one question. Yes, I see one hand raised. Parlapalli is the person. Shravani. Am I audible?
Yes, sir, audible.
Yeah, so the person is on mute, but if there are any other questions, we can certainly take.
Hello.
Hello.
Yes.
So whatever carbon dioxide we are using for refrigeration, these all carbon dioxide are taken from ambient air.
No. So Dr. Kamal Jyoti, see, I would like to just tell you, see, these are processed carbon dioxide. They are from industrial processes. It is not economical to extract carbon dioxide from air and use it. So 90%, I mean, almost all carbon dioxide that have been used for medical grade or refrigerate or essentially food grade carbon dioxide comes from industrial processes. It is a byproduct of many of these processes. You don't create it directly, but it's a byproduct. In fertilizer industries, petrochemical industries, carbon dioxide is typically released.
Okay, means is it possible to use from ambient air?
No, ambient air, your carbon dioxide is very small values. How much is it?
0.03%.
Yeah, 350 ppm, 400 ppm. Maybe
Right,
in cities like Bangalore and Delhi, you might get 1,000, But
right.
it's just not economical.
Okay. Thank you, sir.
You're welcome. Yeah. So,
Hello, sir.
yes, sir. Please tell me.
Sir, I have a very simple question. Is combined power generation and refrigeration cycle using CO2 as a fluid is still only at research level, or does it has been tested on a field also?
No, so essentially, we don't have any published data that has shown that it has been tested in the field, but it is certainly viable, and it is typically used in carbon sequestration. Okay, so where it is cooled and pumped into the ground.
Sorry, sir, which kind of application you told?
Carbon sequestration. So it is being tried out, but it is probably the only refrigerant that will allow you to have a single circuit, where the carbon dioxide is produced, there is a cycle. If you want to read, it's called the Alum cycle. Okay. Alum cycle is called the oxy-combustion cycle, where a hydrocarbon fuel is actually burnt in an oxygen environment. The water is separated out. Carbon dioxide is actually expanded, and then a part of it is cooled, and it is pumped into the ground.
Okay, sir. Thank you.
You're welcome.
Thank you, sir.
Any other question?
Question from Saravanan. How long it will take for the Indian industry to adopt this technology?
Prof. Maiya, I think you would be the right person, or you would like me to answer?
You can answer.
So,
got a lot of practical experience.
So the technology is ripe and it's ready. Okay, so it's just that right now it's a little bit expensive, but we see no hurdles in India, having to adopt it. People talk about efficiencies in terms of the COP, how much it is, but it's like buying a new car. You'll talk about mileage only before you buy the car. After it is, then everybody's car gives good mileage. So it is very similar to that. You will forget about what is COP the moment you have actually built the system. So one thing is that it performs extremely well. Okay, and it's very, very robust, that now you have a lot more metal in terms of the pipe thicknesses and other things. So it is much better well built than 134A or any other systems, by the sheer fact that it is a high pressure system. So a good system of carbon dioxide will become affordable. Controllers are a little expensive, but that's only because the market is not big enough. Once the market becomes big enough, CO2 systems are going to be economically viable. Prof. Maiya, you want to add anything to it?
Okay, good. Answered well. One more question we can answer is, if CO2 systems have performed better than expected, how is the piping wall design considered in industry level? I think they're asking about how to design the piping and other things.
Sure. Yeah, so I can tell you in one your sentence. One is that you can go to any of the standard manufacturers like Swagelok or Sandvik or any of them. They will tell you temperature versus pressure data for every tube that you buy from Sandvik or Swagelok. It's not rocket science. This is the world of internet. All your information is available on your fingertips. 10, 20 years back, you will have to do a simple calculation to find out how much is the hoop stress in the pipe at a given temperature, and you should at least know a little bit on the material properties. But now everything is available online, and if you have access to a ASME piping standard handbook, it'll give you all the more. It becomes easier.
Yes.
Okay, so yeah. So this is so certainly I think that selecting appropriate wall thickness of the pipe should not be a problem, but provided you buy it from a manufacturer who will stick to what is the specifications that are available. So I see, yes, any other questions?
If CO2 refrigerant has higher working pressure, how it can be controlled?
So it is essentially CO2 refrigerant by nature is a high pressure working fluid. No. If you ask an elephant to be thin, then it's not possible, right? So it's similarly a CO2 system. Thermodynamic properties will tell you that the critical pressure being actually at 31 degrees Celsius, and the critical pressure being 78 bar, you have to pressurize it to higher than 78 bar. So there is no other option. So if you want to reduce the working pressure of carbon dioxide, you have to blend it. But then our own experience, we have seen that it does not form something called an azeotropic blend. So that means that you will now have a glide, and that is undesirable for a refrigerant. So we really don't see a benefit of using carbon dioxide in a blended form to reduce the pressure.
Okay, I think there are a lot of good comments appreciating the session. Thank you all for your support and cooperation. I think not many comments on the sessions. Favorable comments, good comments.
Also,
Thank you very much.
on behalf of the organizing committee, as a part of it, also we'd like to thank the audience for their very patient hearing for last 3 years. So we didn't expect that many of them would stay back till nearly 7:30.
So, Dr. Shiva, can we close the session? You can thank the audience and then tell what is tomorrow. What are the talk tomorrow, and then can close the session, please. Dr. Shiva?
Yes, sir. Yes, sir. So thank you all the participants. So now we came to the end for this today's sessions. Tomorrow at the same time, 4 o'clock, we have 3 more lectures. So transcritical CO2 refrigeration system control, there is 1 lecture, and simultaneous milk chilling and pasteurization, and latest developments.
Sorry to interrupt you, but I think you should also announce the speakers for tomorrow.
Yes, sir. Yes, sir. So the first lecture is transcritical CO2 refrigeration system control, a practical approach by Mr. R.P. Kamath from Danfoss. And second lecture is simultaneous milk chilling and pasteurization by Professor M. Ramgopala from IIT Kharagpur. And third lecture is by latest developments in Indy Plus project demo sites by Dr. Simarpreet Singh from NTNU. So these are the 3 lectures will be delivered by tomorrow.
So I would only request, Dr. Reddy, just let me add to that. I think just for the audience who are very serious about carbon dioxide or natural refrigerants, I think tomorrow's 3 lectures are going to be vital, because it'll specifically show about case studies and data that is generated from real systems, and also the potential of market in India for carbon dioxide. And the first one is, of course, from a commercial company, what Danfoss actually has got the portfolio of products specifically tailored towards India system development on carbon dioxide. So I think I don't know whether Mr. Kamath is there, but he is also part of the organizing committee. So yeah, he is there. But so I think these are very important things there if you plan to ever venture into building or understanding a CO2 system. Dr. Shivkumar, sorry, please go ahead.
Yes, sir.
Yes,
sir.
Okay,
yes, sir. Yes, sir.
The session, today's session, and thank you. Please thank everybody, and then close the session. Telling that tomorrow we come online at 4 o'clock, 4 p.m.
Yes, sir. So thank you all the participants for today's workshop. And tomorrow at the same time, 4 o'clock, we will have 3 more lectures. And thank you very much. So we are closing the session. Tomorrow we'll meet again. Thank you.
Thank you all. Good night.
Thank you.
Thank you.
Thank you all. Good night.
Thank you.